Chapter 11 Kinetic Theory of Gases Section 11.1 One-dimensional velocity distribution of gas particles. Maxwell and Boltzmann proposed that the probability of a gas particle moving at a speed between Vx and Vx plus dVx is proportional to a exponential function e to the power of negative kinetic energy in the x direction over kBt. The kinetic energy is half mvx squared in this x direction. The probability of finding the particle moving at a speed within this range can be written as a times this exponential function times dVx. Again, this is exponential function of negative kinetic energy over kBt. dVx is the range, and A is the normalization factor. We can also write the probability to be the product of the probability density within the range multiplied by the range. So this f function is equal to A times this exponential function of negative kinetic energy over kBt. In case of B is the Boltzmann constant. Case of B is the gas constant over the Avogadro constant, and we have the value here. A is here to ensure the integral of this whole thing from 0 to infinity is 1. The physical meaning is simple. The probability of having a particle moving at a speed between 0 to infinity in the x direction is 100%. Again, f is the probability density function. So over here this is f. F is the normalization function multiplied by this exponential function of negative kinetic energy over kBt. Or you may view this as a Gaussian function of this Vx. You can see this Vx is squared over here. So it depends on how you view this exponential term. Now let's look at the definition of the probability density again. This f, the probability density, is equal to, well, the probability of finding the particle moving at a speed within this range and then divided by the range. That's why it's called probability density. Now if we look at the velocity instead of the speed, we'll have a different distribution of probability. Why is that? Well, if you tell me the speed is 5 meters per second, then the velocity can be positive 5 or negative 5. So somehow the probability density of having the positive 5 meters per second versus negative 5 meters per second should be the same. So we have to kind of just divide the probability density of this speed by 2, and then we'll get the corresponding probability density for this positive velocity and this negative velocity. And that's why we have a Gaussian distribution of velocity, symmetrical with respect to 0 velocity in the middle. So you can see on the left we have negative velocity, on the right we have positive velocity. Alright, and then this is symmetrical with respect to a 0 velocity in the middle. Now here we have the probability density of velocity. Maxwell and Boltzmann proposed that the probability of a gas particle moving at a speed between this range is proportional to this Gaussian function of Vx, or you can say exponential function of kinetic energy. And then over here we have the expression for probability. It's the probability density multiplied by the range. The probability density function is the probability of that range divided by the range. The SI unit of probability density is second over meter. It sounds weird, but probability is unitless. On the bottom we have a unit of meter per second. So that's why this probability density has such weird unit. Since the total probability of finding a particle within a speed between 0 and infinity should be 100%, and then we have the integral of this probability density equals 1, and the probability density is the normalization function times, just normalization factor times the Gaussian function of speed. So we can solve this equation to get the normalization factor A. A is 1 over this integral. We just need to know how to integrate this Gaussian function of speed. A common strategy of simplifying an integral is via variable substitution. Somehow, if we can set q is vx times the square root of m over 2kbt, we can simplify this Gaussian function of vx to a much simpler Gaussian function, e to the power of negative q squared. Alright, again, let's look at this. This is mvx squared. Alright, so if we square this part, you get mv squared. On the bottom you have 2kbt, on the bottom you have 2kbt. So if you just take q squared, you get this squared, which is just this part. So again, we'll just have to make sure this integral is 100%, and we set q to be proportional to the speed. It's speed times the square root of m over 2kbt. Now we have q squared is mv squared over 2kbt, and vx is equal to q times the square root of 2kbt over m. And now we have this integral rewritten in terms of q. This Gaussian function becomes e to the power of negative q squared. The vx is just q times this square root of 2kbt over m. So this whole thing is just 1. Q is unitless. You can double check. This Vx is in meter per second, but this square root is going to be in second per meter. So overall, Q is unitless. I'll let you double check. M is in kilogram. kVt is in joule. So kilogram over joule. You will get second squared over meter squared, and then we take the square root of it. Q is unitless, so the lower and the upper limits of Q is 0 and infinity, alright, without any unit. And we can look up the value of this integral of a Gaussian function. It's the square root of pi over 2. You can click this website. Just download my PowerPoint file, and you can just click it. You go to Wolfram Alpha, you see this integral. It's square root of pi over 2. We can also prove this on paper, but you do need to know how to convert from Cartesian coordinates to polar coordinates. So I'm not going to talk about that in this video. Now we just use this integral being the square root of pi over 2 here. And over here we have square root of 2kbt over m, which is a constant. So we put everything here. Now we can express a as the square root of 2m over pi kbt. This is not very convenient when we do numerical calculations, because this m is the mass of one single atom or molecule in the gas phase. So I multiply the numerator and denominator by Avogadro constant. So this ends up A, appears on top and the bottom. And then over here, the Avogadro constant times the mass of one atom is just the molar mass. And over here, the Avogadro constant times the Bose constant is just the ideal gas constant R. So I like to use this equation to compute A. Alright, molar mass on top times 2. On the bottom, it's just pi times R, the gas constant, times the temperature. Again, the lowercase m and uppercase m are the mass of one atom molecule versus the mass per mole such atoms or molecules. Kb is the Boltzmann constant, R is the ideal gas constant. Now we have the normalized probability density. It's over here. It looks a little complicated, but this part is simply a constant at a given temperature because the mass is constant, Kb is constant. And again, because m and the uppercase m differ by Avogadro constant, Kb and R differ by Avogadro constant, so we have this lowercase m over Kb is uppercase m over R. The uppercase m is the molar mass, so we have this function, alright, over here. Now we use hydrogen as example. If we have a hydrogen gas, the molar mass is 0.002 kilogram per mole. I'm using kilogram because this is the SI unit of mass. Gram is not the SI unit of mass. So I just compute molar mass over RT. Okay, the reason is I see molar mass over RT here, I see molar mass over RT there, so why don't we just pre-calculate molar mass over RT? It's this. Okay, it's this. Make sure you have the right units, alright? And then we have the expression of the probability density. You plug in this molar mass over RT here, and over here you get this function. You can see the unit is second over meter. I explained why that is. And you have this equation. If you integrate this over a range for speed from 0 to infinity, you should get 100%. Now let's look at the velocity distribution. The velocity over here is equal to the probability density of negative velocity, alright, because it should be symmetrical. And if you have a speed of 5 meters per second, so it's equally likely to have this particle moving towards the positive direction versus the negative direction. So these two functions are just 1/2 of the probability density of the speed. Again, for each speed, there are two possible velocities. One is positive, one is negative. Okay, either way is possible, and their probabilities are the same. You know, whether it's positive direction or negative direction, it's the same. Now we have the normalized Maxwell-Boltzmann velocity distribution function. Alright, this is also called a probability density function. Same thing, different names. Distribution function, probability density function, they are the same. Now we have this is equal to just 1/2 of the probability density of the speed. Alright, that's why you have this 2 on the bottom versus this 2 on the top. So you have this. We can also just integrate the probability density of velocity. But if you do that, the lower and upper limits are now from negative infinity to positive infinity. It's not from 0 to infinity. It's from negative infinity to positive infinity, because the velocity is signed. It can be negative. Alright, now again, let's use hydrogen as an example. We do similar calculations. We get this expression is just 1/2 of the probability density for speed. Again, lowercase m over kb is uppercase M over r. The lowercase and uppercase m are the mass of one atom or molecule versus the mass per mole particles. Kb and r are the Boltzmann constant, ideal gas constant. And make sure when you do numerical calculations, I'd recommend you to just have all those values in the SI units. For example, molar mass should be in kilogram per mole, not gram per mole. Chapter 11, Kinetic Theory of Gases, Section 11.2, Three-dimensional speed distribution of gas particles. In the previous section, we have derived the normalized probability density function of velocities in the x direction, which is this. F is the probability density function. Vx with an arrow on top is the velocity in the x direction. The square root of m over 2 pi kbt, this is the normalization factor. And over here we have e to the power of negative mvx squared over 2 kbt. This is the kinetic energy in the x direction over kbt. The reason I didn't put an arrow here is just because Vx squared is equal to Vx with an arrow squared. Now let's look at the y direction. We have the same equation, except x is replaced with y. And now we have the same equation for z. All three dimensions, they have the same normalized probability density function. Now, because the motions in the three dimensions are independent of each other, that means how fast a particle is moving in the x direction and how fast it's moving in the y direction do not depend on each other. The normalized three-dimensional velocity distribution function is simply the product of the lowercase f of Vx, f of Vy, f of Vz. So we just need to multiply the three. For example, if you threw 3 dice, the probability of getting, for example, 1, 1, and 1 is 1 over 6 for the first dice, 1 over 6 for the second, 1 over 6 for the third. So you can multiply them together, you get 1 over 216. Alright, that's why we do multiplication here. The probability of 3 events happening at the same time is equal to the product of the probability of event 1 happening at that time multiplied by the probability of event 2 happening at that time multiplied by the probability of event 3 happening at that time. That's the meaning of this. Alright, now we just multiply the 3 probability density functions in the x, y, and z direction. We can see this normalization factor is the same in these 3 equations. So now we have this m over 2 pi kbt to the power of 3/2. And then we have a Gaussian function of Vx, a Gaussian function of Vy, and a Gaussian function of Vz. We can combine this. Over here we have Vx squared plus Vy squared plus Vz squared. What is this? Well, this is simply V squared, and V is the 3-dimensional speed. So actually this probability density function of the velocity in the x, y, and z direction can be rewritten as this simpler function. Again, it's m over 2 pi kbt to the power of 1.5, and then e to the power of negative the 3-dimensional kinetic energy over kbt. The SI unit of this function is a little weird. It's second divided by meter and then to the power of 3. The normalized three-dimensional velocity distribution function can be written as this. We have a normalization function in the front. We have a Gaussian function of the three-dimensional speed over here. And we know this has to be 1 if we integrate the velocities in the 3 dimensions from negative infinity to positive infinity. And we call this dvx, dvy, dvz as the volume element of this triple integral. So really this dvx will be integrated from negative infinity to positive infinity. So will this dvy and dvz. And then we can convert this integral with this volume element in the simple xy coordinates to a more complex spherical polar coordinates. The spherical polar coordinates of 3D speed depends on 3 things. 1, the magnitude of the 3-dimensional speed, and 2, the angle between the velocity vector and the z-axis, and 3, there's another variable. So if you project the 3-dimensional vector to a xy plane, then you get a 2-dimensional vector, and between the 2-dimensional vector and the axis we have the third variable. We call that phi. Alright, so the volume element of the spherical polar coordinates of 3D speed is this. It's v squared sine theta dv d theta d phi. We will prove this in the next slide. Now let's look at this. We have this equation. Alright, this is equivalent to this equation. It's just we changed the orthogonal Vx, Vy, Vz coordinates to a spherical V, theta, phi coordinates. V is from 0 to infinity because V is now the 3-dimensional speed. Theta is the angle between the velocity vector and the z-axis, and theta is from 0 to pi. Finally, phi is the angle between the x-axis and how the velocity vector being projected onto the xy plane. Now we have this integral equivalent to this integral, so the value should be 1. And we can plug in the expression of this uppercase F over here. Okay, this is a Gaussian function of the 3-dimensional speed. So really this should be 1, 100%. And theta and phi are corresponding to the latitude and longitude of a sphere. It's just when we are talking about Earth, the latitude is usually from north 90 degrees to south 90 degrees, a span of 180 degrees in total. We have also a span of 180 degrees in total, or pi. Longitude, if we're talking about the geography, I think it's usually from west 180 to east 180, with a range of 360 degrees. And over here we have a range of 360 degrees, which is just 2 pi. The speed ranges from 0 to infinity. Over here it's just because we want to integrate all possible speed. Now we're going to answer this question: why is the volume element v squared sine theta dv d theta d phi with this kind of limits? We'll have to look at 2 graphs. I'm going to use XYZ for a simpler explanation. in a Cartesian coordinates, the volume element of space is dx, dy, dz. If you try to integrate over the entire space, we just need to integrate dx from negative infinity to positive infinity. dy also, we have y from negative infinity to positive infinity. And so does this dz. In the spherical polar coordinates, however, we're going to have to do things a little differently. So this box-like shape is the volume element in the polar spherical coordinates. So we're going to approximately get the volume of this, alright, by assuming this is indeed a box with 3 side lengths. This side length is dr. So first you have r, and then you extend it by an infinitesimal amount, which is just dr. Alright, this is dr. And also we're going to just draw an arc. This is theta, so from here to here it's theta. Theta is the angle between this vector and the z-axis. We're going to extend it by an infinitesimal amount from theta to theta plus d theta. And then this arc is simply r times d theta. So now we have dr and then also r d theta. This one is a little bit tricky because it contains 3 components. You do have r sine theta and d phi. So if we project this 3-dimensional vector onto the xy plane, the length over here is r sine theta. This is r sine theta. And then we have an angle phi here. And we can extend this phi just a little bit to phi plus d phi. And then, we can rotate this a little bit more, which is d phi. D phi times this radius give you this third side length. This radius is r times sine theta, and then multiplied by the angle d phi. We got the third one. Now we just multiply dr, r d theta, r sine theta d phi all together. You get r squared sine theta dr d theta d phi. So this is why we have this kind of volume element for the 3-dimensional speed. Okay, and over here we can just simply replace r with v. We get this volume element for speed. Now the integral of the normalized probability density function must be 1. So we have this is 1. Alright, and we can separate the variables. We see 3 different variables: v, the 3-dimensional speed; theta, the angle between the velocity vector and the z-axis; and phi, well, you have to project the velocity onto the xy plane and then find its angle with x. So you have v is from 0 to infinity, theta is from 0 to 2 pi, phi is from 0 to 2 pi. Alright, so we have this. Now let's separate the 3 variables. We have 3 single variable integrals. Over here, an integral of v, an integral of theta, an integral of phi. The integral of phi is simply just 2 pi. The integral of sine theta is negative cosine theta from 0 to pi, and the result is 2. So this is 2, this is 2 pi, together you have 4 pi. And also, if you compare this equation with the previously learned probability density function in the coordinates of vx, vy, vz, we have one additional term, which is v squared over here, v squared. Alright, now we have the probability density of gas particles moving at a 3-dimensional speed within this range, v to v plus dv. It's this. Note that this v is the three-dimensional speed. All right, and dv is the differential of the three-dimensional speed, and then we have this equation. So it's not simply the uppercase F anymore in the Vx, Vy, Vz coordinates. We do have additional terms. We have V squared here, we have 2 here, we have 2 pi here, and together it's 4 pi V squared. The uppercase F, again, is just this, alright? It's just the distribution in the x direction multiplied by y direction multiplied by z direction. So that's why we have this thing to the power 1.5 and e to the power negative mv squared over 2 kbt, and this v squared is vx squared plus vy squared plus vz squared. So we just have one additional term, 4 pi v squared here, when we are examining the probability distribution of the three-dimensional speed between v and v plus dv. So it's going to be this. Well, again, if you have a gas particle, the probability of finding the particle moving at a speed from here to here is simply its probability density multiplied by the range you're given. The range is dv, so really it's just this times dv. Alright, now what if we need to find the most probable three-dimensional speed? We'll have to just maximize this equation. How do we maximize the equation? Well, at the maximum, the slope should be 0. So we're going to just take the differential of this equation. It looks a little complicated, but it's doable. This part is constant. It does not depend on v. 4 pi does not depend on v. So we're going to just evaluate this. I'm going to use the product rule. V squared goes to 2v, that's the first derivative, and over here I need to get the derivative of this Gaussian function of v. So I'll copy v squared here, right, and now I'm gonna view this whole thing as a variable. I set a variable, maybe alpha to be this, so e to the power of alpha. I just copy that e to the power of alpha here. And now I need to take the derivative of alpha with respect to v. Is this. Alright, it's just variable substitution and also the chain rule in calculus. How do we solve this equation? First, the Gaussian function and Gaussian function, well, we can make them disappear. Just both sides of the equation divided by the Gaussian function, right? And then we have 2v and then minus mv cubed, v squared times v cubed over kbt. Solve this, we get the most probable three-dimensional speed. Alright, it's the square root of 2 kbt over m, or square root of 2RT over uppercase M. M is the molar mass in kilogram per mole. Let's look at helium as an example. The square root of 2RT over M, 2 times R times temperature over the molar mass of helium in kilogram per mole. We get 1100 meters per second. It's really fast. Well, the probability density distribution function, or simply probability density function of the three-dimensional speed v is this. Again, don't forget about this 4 pi v squared term. If you don't remember this, actually this is simply the surface area of a sphere that has a radius of v. That's just 4 pi v squared. So really, if we multiply this 4 pi v squared by dv, you're gonna get a volume of a shell. The shell has a thickness of dv. The spherical shell has a radius of v, and then you can probably better understand this 4 pi v squared. Now we have this. Given this, we can also compute the average speed and the root mean squared speed. The average speed is actually the probability weighted average. Alright, so this is average. By the way, the average can be denoted by a pair of bracket, a bar on top, or AVE, in the subscript. Either way, so these three are just notations for the average speed. To do that, so we have this speed, right? We have speed over here, and then over here, from here to here, that's the probability of finding a particle moving at a speed between v and v plus dv. So we have this. So this is v times the corresponding probability, and we integrate everything. That's the physical meaning. The problem is this: how do we integrate this? It looks very complicated. We always simplify the Gaussian function first. What I'm going to do is I'm going to simply set q to be mv squared over 2kbt. So I'm setting this whole thing to be q. So you get e to the power of negative q. Alright? And then because of this, v squared is just 2kbt times q over m. And then v is simply the square root of this. Now we can simplify everything. So first, we write out the average speed over here in terms of v, and then I will start to replace this whole thing with q. V squared is just this guy, dv squared is just the differential of this guy. So now we have this equation. We can of course take 2kbt over m out. We take this out as well, so you see this twice. I copied 2 pi here, I copied this m over 2 pi kbt to the power of 3/2 here. Alright, and then we have a very simple integral right here. It's a very simple integral. It's just e to the power of negative q times q. You can do this by hand if you're good at calculus. Mostly you just need to move this into this d and then use the product rule. Alright, but now I'm gonna just give you the expression of this integral. It's this: plug in 0 and infinity, the result is 1. So this integral is just 1. And then we combine all other terms. Alright, all other terms. You do have kbt on the bottom, and it's kbt to the power of negative 1.5. Also you have kbt and another kbt, so it's going to be kbt to the power of 1/2. You have mass to the power of 1.5, but over mass squared, so you have this mass on the bottom inside the square root. You do have a pi here, and you have pi to the power of negative 1.5, so you have pi on the bottom. You have a 2 here, you have a 2 here, you have a 2 here, that's 8. But also you have this one. This one is actually 1 over the square root of 8, so you have the square root of 8 over there. Yeah, from here to here, it is tedious, but it's very simple algebra. If you are patient enough, you can go from here to here. And this integral is simply 1. You do need to know how to do the evaluate this. The probability density function of the three-dimensional speed is this. Again, it's this. Now let's look at the probability weighted average of v squared. Well, sometimes we'll just say, well, this is just a root mean squared. Why? Because we square this v first, and we take the average, and then we take the square root. Alright, so it's right here actually. Root mean squared. We have the speed squared first, that's why I squared here. And this bar means average or mean. And then a square root over here, that's root. So that's why this is called a squared root mean squared, or RMS speed. Now let's look at this. The probability density function is given over here. Now let's look at the average of v squared. It's just this. We put v squared here, and this is the probability of finding the particle moving at a speed between v and v plus dv. So this whole thing is the probability. Okay, without dv, that's probability density. With dv, that's the probability. Alright, the probability weighted v squared, you integrate this. And again, we just set variables to make things easier. What I'm going to do is I'm going to set this whole thing to be q squared. Okay, this whole thing to be q squared. So q is just the v times the square root of m over 2kbt. And of course, correspondingly, v is q times the square root of 2kbt over m. So you use this equation to get this equation. Now we have this integral written. From here to here, a bunch of algebraic operations. I think I copied 2 pi or 4 pi to here. I copied this to here. Where does this come from? This comes from, I think it's just because V is Q times this thing. So you have this thing squared, and over here you have that thing again, and over here you have this thing that's squared. So squared to the power of 1, so overall to the power of 5. So we need this to the power of 5. That's this. And now the integral is simply e to the power of negative q squared times q of q to the power of 4. This is not trivial. I didn't want to do this by hand. It's doable, but I used the Wolfram Alpha. So if you just download this PowerPoint file, you can click this. You can see how Wolfram Alpha tackled the problem. The value is 3 over 8 times the square root of pi for this integral. If you really want to do it by hand, it's doable. It's just we will keep lowering this power, until the power becomes 0, and then we know the integral of e to the power of negative q squared dq from 0 to infinity is square root of pi over 2. That can be proven, but it's really tedious to tackle this integral, so I'm gonna just use the value from Wolfram Alpha to put it in here. I combine everything here, it's this, and then in the end we got this. Finally, the root mean squared 3-dimensional speed is the square root of this guy. It's the square root of 3 kBt over the mass. And just because v squared is the sum of vx squared, vy squared, and vz squared, and also the distribution in the x, y, and z directions should be the same. So when you see this, you should just give 1 kBt over m to vx squared, 1 kBt over m to vy squared, and 1 kBt over m to vz squared, and then you have 3 of them. Alright, so if you're looking at the root mean squared 1-dimensional speed, well, it's just square root of kBt over m. You can prove this as well, given the distribution in the x direction. You can prove this as well, but I'm not gonna do that. This is to summarize the 3 different quantities. We have the root mean squared 3-dimensional speed, we have the average 3-dimensional speed, we have the most probable 3-dimensional speed. They share something common. They all have the square root of kBt over m, kBt over m, kBt over m. They do differ by the number in the front. You have 3 here, you have 8 over pi here, you have 2 here. The square root of 3 is 1.732, the square root of 8 over pi is 1.596, the average is 1.414, and you can see this is larger than this is larger than this. Now let's look at a numerical example. Let's look at the RMS, root mean squared, average, and most probable speeds for the nitrogen gas at room temperature. It's more convenient to pre-calculate the square root of kBt over m, so I did that here, and then multiplied by the square root of 3, we get the RMS speed. Multiplied by the square root of 8 over pi, we get the average speed, and also multiplied by the square root of 2, we get the most probable speed. And you can see the order of the 3. 515, 475, 421. Alright, so there's 3 numbers. You can just do a simple calculation yourself. Let's say there are only 3 particles moving, and their 3-dimensional speeds are, for example, 1 meter per second, 2 meter per second, and then let's say 6 meter per second. 1, 2, and 6. And then somehow you can just compute the root mean squared and the average. You'll see this is always greater than this. Alright. For the most probable speed, well, you need more data point. Again, let's look at the three equations. Most probable, average, root mean squared. They share something in common, which is the square root of kbt over m. Square root of kbt over m. They differ by a coefficient. Square root of 2, square root of 8 over pi, and square root of 3. They are just 1.414, 1.596, 1.732. Alright, and now let's look at some distributions of the speed at different temperatures. Low temperature 100K, high temperature 1200K, really high temperature 3000K. This is the distribution of the speed at different temperatures. You can see at lower temperature 100K, this distribution is narrower. Alright, and the average is this is average, this is most probable, this is RMS. Those are in the lower end. Now if you increase the temperature, we have most probable, average, and RMS speed. Okay, higher numbers. Finally, 3000 Kelvin. Again, the same order, most probable, average, and RMS. Much larger numbers over here. Just to summarize, at low temperatures, the distribution is narrower. At higher temperatures, the distribution is wider. And also toward the high speed range. You can see, some molecules move at 3000 meter per second over here. Over here, at most for this 100 Kelvin, roughly 1000 something. Over here, more than 3000. We also need to look at another factor, which is the mass. We did see temperature on top, so if you have a higher temperature, you have a larger RMS, average, and most probable speeds. But what if you have a larger mass? M appears on the bottom, so larger mass means slower particles. You're gonna get smaller numbers. Now let's look at the distribution of three speeds. For helium, neon, argon, and xenon, you have the mass numbers 420, 40, 132. You can see over here, this is xenon, argon, neon, helium. Helium has a wider distribution because it can span into the really high speed region. So over here you can still see a decent probability density over here, and look, it's in the unit of second over meter. So again, second over meter. Alright, so over here, this is just because the unit of this is the unit of probability divided by the unit of the range of the speed. The unit of the range of the speed is meter per second. The unit of probability is okay, it's unitless, so that's why you have this. Right, for helium, it's possible to have a decent probability with like 2500 meter per second. Neon, so about here. Okay, the high-speed neon molecules, high-speed argon molecules, and atoms, high-speed xenon atoms. And also, it's really easy to find the most probable speed. So that means just the maximum probability density. So we find out here, here, and here, and here for xenon, argon, neon, and helium. So if you take the ratio between those probability density, it's going to be the square root of 1 over 132 versus the square root of 1 over 40 versus the square root of 1 over 20 versus the square root of 1 over 4. You see, this is proportional to the square root of 1 over the mass. So we can make quick predictions. If you compare just neon and helium, neon weighs 5 times that of helium. Therefore, you can see helium is the square root of 5 times of the speed of neon. And you can also compare argon and helium. They differ by 10. Therefore, those speeds differ by the square root of 10, with the lighter gas particles traveling faster in general. Chapter 11, Kinetic Theory of Gases, Section 11.3, Collisions and Pressure. Pressure results from the collisions between the gas particles with the surface areas inside a container. We will be able to derive PV equals nRT for ideal gases, assuming all collisions are elastic. We will look at the motions of one individual gas particle and then extend it to all gas particles inside the container. And you can see over here all those particles are colliding with the surfaces. During the collision, the momentum of the colliding particle changes, and that change is due to the force exerted by the surface area and the particle. And force divided by the area is pressure. So now let's do the derivation. Let's study n mole argon atoms in a box. Let's say the side length of the box is L. Alright, over here in the x direction. And this box has a bottom area of A. So the volume is A times L. Now we'll just look at one particle, and we will look at the motion of this particle in the x direction. We know the average kinetic energy of each atom in each dimension is 1/2 kBt. This is from the previous section. In the previous section, we derived the root mean squared speed, which is the square root of 3 kBt over m. Therefore, the average kinetic energy of the particles is 1/2 of the average of mv squared, and this is equal to 3/2 kBt. So really you just need to square this. Alright, you square it, you get this, multiply by m. Alright, multiply by m, and then divided by 2, you get 3/2 kBt. And that's the average kinetic energy of the gas particles. Now we're going to assume the x dimension, y dimension, and z dimension have the same distribution of the speed. And then we have this in each dimension. The average kinetic energy is 1/2 kBt. In 3 dimensions, we have 3/2 kBt. 1 dimension, just 1/2 kBt. And now we're going to just look at the collision between this single particle and this shaded area, A1 area, and see if we can derive the expression of pressure. And eventually we will get pressure equals nRT over volume for the ideal gas. Within delta t, time period delta t, an argon atom can travel first to right as indicated by this arrow and collide with the shaded area, change its direction, collide with the A2 area, change its direction, get back to the original position, and keep doing the traveling. How many times? Well, this particle will have to travel a total distance of 2L to return to its original position. So let's look at this. We're going to move this particle to this area, change its direction, change the direction again after another collision, and get back. So you just need to sum up the length of the first black arrow this arrow and this longer arrow and this arrow. Overall, this is L and this is L. Therefore, this particle will need to travel a distance of 2L to return to its original position. I'm going to call this a travel of 2L as just one collision cycle, because during this one collision cycle, this particle collides with A1 once, it collides with A2 once. But now let's just focus on this shaded area A1. So this particle moves in this direction and bounces back. And then how many collisions take place within this time period? Well, again, we know this particle needs to travel a distance of 2L to have one collision with this A1. So really, if we know the total distance this particle travels divided by 2L, that would be the number of collision cycles and also the number of collisions between the particle and the A1 shaded area. Therefore, the number of collisions between this atom or this molecule or gas particle and the shaded area within time delta t is the distance it travels within delta t, which is Vx times delta t divided by 2L. So that's the analysis. The number of collisions within delta t between the particle and A1 area. Well, you may wonder, this particle might also moving in the y direction and also z direction. That's true. It's just we do not care about the motion of the particle in the y direction or z direction. We're just focused on the x direction. Even if this particle moves in the y or z directions, it does not change our analysis here for the number of collisions between the particle and the A1 area within time delta t. Now, each collision between this atom and this surface area results in a momentum change of this particle. It's just because we assume the collision is elastic. So before the collision, the speed is Vx. After the collision, the speed is also Vx. However, the velocity changes. It goes from positive Vx to negative Vx. Or if you define the direction in the opposite way, it changes from negative Vx to positive Vx. So the magnitude of the change of the momentum should be 2 mvx. It goes from negative mvx to positive mvx, or from positive mvx to negative mvx. Either way, the magnitude of the change is 2 mvx. Now we have this number of collisions. Alright, for each collision there's this much momentum change. So we're going to multiply these two together. That's going to be the total momentum change caused by this A1 surface area to this particle within a time period of delta t. Now let's look at this equation. 2 and 2 cancel. Vx times Vx. We have mvx squared on top, delta t on top, L on the bottom. Again, within delta t, the total momentum change of one particle is this. But what if we have MO particles? When we have MO particles, we have n times Avogadro atoms or molecules or particles. So we have to kind of sum up all this for all particles. It's going to be the sum of mv squared delta t over L. This I is the index for the atoms in the gas phase, or the particles in the gas phase. I is from 1 to n times Avogadro constant. So again, this is just the total momentum change of all gas particles caused by the collisions between the particles and this A1 area, shaded area. Again, the total momentum change caused by the A1 surface and the particles within time delta t is this much. Over here we have the sum over all particles. Alright, and we can clean it up because M, delta T, and L do not depend on I. So I'm taking those out. Now we have just the sum of V squared for all the particles. Well, remember the sum of many data is just the number of data multiplied by the average. Right? This is the sum, this is the average, and this is the number of data. So that's why we got this here. Since the root mean squared speed is the square root of 3 kBt over m, we have this equation by having the left side squared and the right hand side squared. In each of the 3 dimensions, we have Vx squared equals Vy squared equals Vz squared, which is just 1/3 of this, which is just kBt over m. The total momentum change over here between the particles and the A1 shaded area is thus over here. I was replacing mv squared with kBt. And note here the Avogadro constant times the Boltzmann constant is equal to R, the ideal gas constant. So we have this simple equation. That's the total momentum change of all gas particles caused by the collisions between these particles and the A1 shaded area. And Newton's law tells us we can't just change the momentum of the particles without any force. We need a force, and we need a period when this force exerted to those particles. So this momentum change is due to the force during this time period. So now you can see we have delta T on the left and right sides. Both sides divided by delta T, we have nRT equals FL. This allows us to determine the pressure, because force is pressure times the area. And now we have nRT equals P times the surface area of A1, the shaded area, times the length of the box. A times L is the volume of the container. Now we have PV equals nRT. In the above derivation of PV equals nRT, we assume that there is no attraction or repulsion between the gas particles. Therefore, the momentum change of the particles are caused only by the collisions with the surface of the container. But what if there is attraction or repulsion? The attraction between the gas particles reduces the momentum change of the particles in collisions with the container surfaces, and therefore lower the amount of force and lower the amount of pressure. Well, this is also how seatbelt works in a car accident. In a car accident, well, the driver is likely to hit the windshield. But what if you have the seatbelt pulling the driver away from the windshield? It's almost like attraction pointing towards the center of the car, away from the windshield. And now, even when a collision between the driver and the windshield transpires, the severity of the collision is reduced by the pull from the safety belt. Similarly, when a particle is about to collide with a surface, if all other gas particles are attracting the colliding particle, it's going to reduce the magnitude of this collision and lower the pressure. On the other hand, repulsion between the gas particles increases the momentum change in the collisions with the container surfaces and then elevates the pressure. Let's use the car accident as another example. Repulsion is almost like someone pushing you from behind when you are about to hit the windshield. And if there's no attraction between the gas particles, let's just focus on this repulsion. That means you're not wearing the seatbelt, no attraction towards the center of the car, only repulsion that pushing you from behind toward the windshield. And that push or repulsion would increase the pressure between you and the windshield. That will increase the severity of the collision. You will have higher pressure. In summary, attraction between the gas particles reduces pressure. The repulsion between gas particles increases the pressure. And we can quantify this statement in the Van Hoff's equation. P is RT over molar volume minus B minus A over molar volume squared. So when A is larger, you have more attraction, P is smaller. When B is larger, well, you have more repulsion. P is larger. So again, when A increases, P decreases. When B increases, P increases. Attraction reduces pressure. Repulsion increases pressure. And this statement is quantified in this Van Hoff's equation. What if A is 0, B is 0? Well, then you have the ideal gas equation. In the Van Hoff's equation, B is also a measure of the size of the gas particles. The larger the size of the particles, the larger the value of B. In the ideal gas equation, we are assuming the size is just 0. But what if we're looking at real gas particles with a finite size? In that case, the collisional frequency is higher than the ideal gas just because the traveling distance between two successive collisions would be less than 2L. So very often you do not have to travel the whole 2L distance to get back to the original position. It's because the particle may collide to the surface, change its direction, but not all the way to the opposite surface. Maybe over here it collides with another particle and changes its direction immediately. And that means the particle can just hit here and then hit to another gas atom and change its direction and get to its original position without traveling the whole distance of 2L. That means you have a higher collisional frequency, and that means you have a greater force on the surface area and a higher pressure. Finally, something trivial. In the derivation of PV equals RT, we assume there's no gravity. But if we consider the gravity, then the up motion of the particles should be slightly slower than the down motion, right? Due to the gravity. And therefore, the momentum change caused by the collisions with the top surface is smaller than the momentum change caused by the collision with the bottom surface. Alright, so if a particle is moving up, right before the collision, I think its speed is pretty small. It's smaller than average, and when it collides to the bottom, the momentum is probably greater than average, all due to gravity. And because of that, the air pressure on top of the Mount Everest is lower than the pressure at sea level. Chapter 11, Kinetic Theory of Gases, Section 11.4, Collisional Frequency between gas particles. Gas particles move in all directions and collide with each other frequently. Assuming there are n mole argon gas in a container with volume V and temperature T, how many collisions does one argon atom experience on average within a time interval delta T? To answer this question, we need to define a collision cylinder or collisional cylinder that encloses the traveling trajectory of one gas particle of interest. So in this figure, we will study the number of collisions this red sphere is about to experience. Assuming this red sphere is moving in the horizontal direction from left to right, Now we're gonna examine the other particles. We have a total of 12 particles over here. And now you can see we have 5 blue spheres and 7 green spheres. What's the difference? If you look at the blue spheres, their centers are within this cylinder in the dashed line. If you look at the green spheres, their centers are outside this cylinder. And why do we need to separate these two different kinds of spheres? One in blue, the other in green. Well, it's just because we're just imagine the traveling of the red sphere from left to right. And in this cylinder, we have a radius of 2r. And r is the radius of one gas particle. So from here to the center, that's r. And from here to here, that's r. Alright, so we draw a cylinder that encloses the trajectory of this moving particle. And this cylinder has a radius of 2r, where r is the radius of a single gas particle. Now what will happen is this. If we look at the trajectory of the red sphere, when it moves to this direction, alright, it's going to collide with this blue sphere, right? And assume this red sphere keeps moving, it's going to collide with this sphere. How do we know that? Well, it's just because the radius of this cylinder is 2r. And over here you can see this is more than r and this is r. The sum of this one and this one is more than 2r. So inevitably there's going to be a collision between the red sphere and the blue sphere. Same here. Same for this one. Again, you just need to imagine this red sphere is moving to here. Alright? Now there's an overlap between the red sphere and blue sphere. That indicates a collision. And same here. But if you look at the green ones, well, this one will not collide with this one. So let's say the red sphere is moving towards here. At this position, there's no collision between the green one and the red one. How about here? Well, it's closer, but still, you just mathematically compute the distance between the center of this red sphere, somewhere here, the green sphere, somewhere here. You can see the distance between these two centers are greater than 2r. That means this green sphere is too far away from the trajectory. So mathematically, if we find a particle with its center inside this collision cylinder, a collision may happen. If the center of a particle is outside the cylinder, no collisions. The average speed of a gas particle is this, the square root of 8 kVt over pi amp. We derived this in section 2. The average relative speed between two such particles is different. Assuming both particles are moving, they can move toward each other, they can move away from each other, there can be a orthogonal angle, 90 degrees. So on average, if we integrate all possible probabilities, the relative speed between two particles is the square root of 2 times the average speed. The length of the cylinder within time delta t is therefore square root of 2 times the average speed times delta t. Alright, so from here to here, that's the length of the cylinder. That's also the distance this red sphere is about to travel within time delta t. It's not just the speed of the relative of this red sphere. It's the relative speed relative to the other particles. So we need to have a correction here. Square root of 2. Among all gas particles, the ones with their centers inside the cylinder, so all those blue ones, will collide with the moving atom in red color. The radius of the cylinder is again 2r. That's just the sum of the radii of the two colliding particles. If we have only one type of particles, well, it's pretty simple. It's just 2r, 2 times the radius. Okay, later we'll see if we have two different types of particles. The radius of the cylinder is going to be the sum of the radius of type 1 plus the radius of type 2. We can also calculate the area of this cylinder, which is just pi d squared, and this d is just 2r. Alright, and this circular area of the collision cylinder is called collisional cross-section area, denoted by sigma. So sigma is pi d squared, and d in this case is 2r. Now what if you have two different types of gas particles? So this is type 1, and all other particles are type 2. Now the radius of the cylinder is r1 plus r2. The collisional cross-section area is sigma. Sigma equals pi times r1 plus r2 squared. Again, we just need to sum up the radii of these two types. And in this picture, assuming this yellow sphere, the smaller one is moving from left to right, it's about to collide with only 4 spheres. Alright, over here 5 spheres, over here 4 spheres. And why is that? You can see this radius is smaller than the radius of the red sphere, and therefore we have a thinner cylinder. And then there are fewer particles with their centers inside this thinner cylinder. The smaller the cylinder, collisional cylinder, the fewer gas particles with a center inside the cylinder. Now the volume of the collision cylinder of a moving argon atom is the length of its traveling distance within a time period of delta t. So it's this, square root of 2 times the average speed times delta t. Again, the square root of 2 is placed here because we're talking about the relative speed between two gas particles. And over here, two identical atoms, such as two argon atoms, they have the same average speed. And if we integrate over all possible orientations, the two argon atoms can move towards each other, and then the relative speed is 2 times v average. They can move away from each other, right? And also they can move in the same direction, and they can move in orthogonal directions. So overall we have this as the average speed multiplied by delta t as the typical length of the collision cylinder. The bottom area, or the circular area, is pi d squared, and d is 2r. So we have this equation. Now we have the volume of the cylinder, which is just the length multiplied by the circular area, and the average speed is the square root of 8 kBt over pi m. So we have this expression for the volume of the cylinder. Now, why do we need the volume of this collision cylinder? Well, it's just because it is difficult to count the number of collisions, but it's easier to calculate the number of argon atoms with their centers inside the collision cylinder. How do we do that? Well, we just need to know the number density of the argon atoms in the entire container, and then multiply it by the volume of the cylinder, and that will give you the number of argon atoms with their centers inside the cylinder. We're assuming the homogeneous distribution of those argon atoms in space. Alright, so for example, if we have 1 million argon atoms within a 1 cubic meter container, and we can compute its density. It's 1 million per cubic meter. And then if you have a collision cylinder with a volume, for example, 10 to the power of negative 3 cubic meters, we know roughly the number of argon atoms in 10 to the power of negative 3 cubic meters is 1,000. It's going to be a million per cubic meter times 10 to the power of negative 3 cubic meter, and that's 1,000. And from the previous diagrams, you can see if a particle has its center inside the cylinder, there's going to be a collision between these two, between these two, between these two, between these two, between these two. If the center is outside the cylinder, no collisions. So really, we do not have to count the number of collisions. We just need to know the number of atoms inside the collision cylinder. That's simply the number density N over V multiplied by the volume of the cylinder. N is the total number of atoms in the container, V is the total volume of the gas container, N over V is the number density. So over here we have this as the volume of the cylinder, the length of the cylinder multiplied by the circular area, and then multiplied by the number density. All this is the number of collisions the moving gas particle will experience within a time period of delta t. Alright, so all this has a physical meaning. That's the number of collisions the moving argon atom experiences within delta t. It's the length of the cylinder times the circular area of the cylinder times the number density. Well, of course, the denser the gas is, the larger the gas particles are, or the faster the gas particles move, the more collisions will occur within that time period. So mostly we're talking about this. If N over V is larger, or if D is larger, or if the average speed is larger, and then we have more collisions within a given time period. And now on average, when there's only one type of gas particle, each particle on average undergoes this many collisions within the time interval delta t. And therefore we can compute the collisional frequency denoted by lowercase c sub 11. C sub 11 means the collisional frequency experienced by one particle, and this 11 means type 1 and type 1 collision. So we have the number of collisions within delta t divided by delta t, and that's the frequency. And over here you can see it's square root of 2 times the average speed times the collisional cross-section area times the number density. Again, 11 is not 11, it's type 1 collision. Later we will use Z sub 12 for type 1 type 2 collision. Again, the average speed is V sub AVE. The square root of 2 is to take the relative average speed into account. Pi d squared is the collisional cross-section area denoted by sigma. And in general, larger atoms have a larger sigma. But if we really analyze the collisional frequency between argon and helium, yes, argon is larger. The collisional cross-section area of argon is 1.7 times that of helium. So over here, this pi d squared for argon is larger. But the average speed of helium is larger than argon. So this one is 3.2 times of argon. So overall, if we consider both sigma and the average speed, we'll see very often larger atoms have a lower collisional frequency. Smaller atoms often have a larger collisional frequency. Assuming this N over V is the same, we can estimate N over V given the temperature and pressure of the gas using the ideal gas law. N is the number of moles times Avogadro constant, and the number of moles over volume of the container is just P over RT. So the number density is the pressure times the Avogadro constant over RT. Now let's look at the collisions between two different types of gas particles. Let's focus on this yellow sphere. It's going to move in this direction. We drew a collisional cylinder with a radius of R1 plus R2. R1 is the radius of the yellow sphere. R2 is the radius of the blue sphere and green spheres. So we can see these four blue spheres have their centers inside the cylinder. So the yellow sphere is about to collide with the blue ones, but not the green ones, because the centers of the green spheres are outside the collision cylinder. So we can write out the collisional frequency for this this yellow particle. It's the average speed times the collisional cross-section area, pi d squared, times the number density of type 2 particles. Alright, so again we just need to have this volume and then the number density of type 2 particles. D12 is this radius of the cylinder. It's R1 plus R2. V12 is the average speed. So this relative speed is the speed of R1 relative to the speed of type 2 particles. So V12 is equal to the square root of V1 squared plus V2 squared. To memorize this equation, you kind of just assume V1 and V2 are orthogonal to each other, and you just need to sum up two vectors that are orthogonal to each other, and it's this equation. What if a gas particle is not spherical? How can we get the radius? Well, we can still estimate the radius of a non-spherical gas particle. For example, water is not spherical, oxygen 2 molecule is not spherical, but in this case we can simply define R to be the radius of the smallest sphere that can fully contain the non-spherical particle. So whatever sphere that can contain this O2 molecule, its radius is roughly 2 times the radius of an oxygen atom. Alright, so if you have a molecule with a non-spherical shape, you just need to find 2 points on the molecule that are the farthest away from each other, and that will be the diameter of the sphere that can contain this entire molecule. And again, V12 is the relative speed, and after we put a bar on top, this is the average relative speed. That's the square root of V1 squared plus V2 squared. Both are average speed. And the collisional frequency between type 1 and type 2 particles can be calculated this way. It's N1 times the lowercase c12. So the lowercase c12 is the collisional frequency for one type 1 particle. But we have N1 such particles, so we simply just use this N1, the number of type 1 particles, multiplied by the number of collisions experienced by each type 1 particle within a unit time. So we get this equation. But this equation is not very useful. This is an extensive property that that changes with the size of the system. So for convenience, we want to have a intensive probability that does not depend on the size of the system. So really we define this uppercase Z12, which is the total collisional frequency between all type 1 molecules and all type 2 molecules, and then divided by volume, so per unit volume here. And this way we have an intensive probability over here. And this can be written as the average relative speed times the collision cross-sectional area times the number density of type 1 and the number density of type 2 molecules. N1 over V is the lowercase n1 over V times the Avogadro constant. And the lowercase n1 over V is just P1 over RT, based on ideal gas law. Similarly, N2 over V is P2 over RT times Avogadro constant. And therefore, if we are given the temperature, the partial pressure of type 1 particles, the partial pressure of type 2 particles, we will be able to get this uppercase Z12. The physical meaning of this is the total number of collisions between all type 1 particles and all type 2 particles per unit time, per unit volume. So it's here. And the expression is this. Again, it's the same as this one. It's just N1 over V is P1 times Avogadro constant over RT. Again, the total collisional frequency per unit volume between type 1 and type 2 particles can be expressed this way. The average relative speed times the collision cross-section area times the number density of type 1 and number density of type 2. And this is the formula for the average relative speed. Over here, V1 is 8 kBt over pi m1, V2 is 8 kBt over pi m2. We combine this, we get the square root of 8 kBt over pi mu. And mu is the reduced mass of two particles. And you can tell 1 over m1 plus 1 over m2 is just 1 over mu. This is how mu is defined. Mu is smaller than m1, mu is smaller than m2. Type 1 particles also collide with each other. So there is type 1 collision. The equation is like this. The uppercase Z11 is 1/2 of the number density of type 1 times lowercase z11. Why do we need this 1/2? Well, it's just because when two particles of type 1 collide, without having this 1/2, we will count this collision twice for both particles. So we need this 1/2 factor to avoid double counting. Similarly, the uppercase Z22 is 1/2 of the average relative speed between type 2 particles, multiplied by the collisional cross-section area, multiplied by the number density of type 2, and then again the number density of type 2. So the total number of collisions is actually all those together: uppercase Z12, uppercase Z11, uppercase Z22. So that's the total number of collisions per unit time per unit volume, or the total collisional frequency per unit volume. For bimolecular reactions between type 1 and type 2 particles, we don't care about Z11 or Z22, we care about Z12, because only the collisions between type 1 and type 2 result in a chemical reaction. So the reaction rate should be proportional to this uppercase Z12. And you can see the reaction rate should be proportional to the number density of type 1, the number density of type 2, the average relative speed, and how large those molecules are. For the bimolecular reaction between type 1 and type 2 particles, the reaction rate R is proportional to uppercase Z12. Uppercase Z12 is the collisional frequency between all type 1 and all type 2 per unit volume. And the expression is this. Not all collisions result in a successful reaction because we need to consider two more factors: the energy factor and the entropy factor. So first, the energy factor. The probability of the colliding particles having enough energy to overcome the reaction barrier has to be considered, and that's the energy factor. And the probability can be computed using this equation: e to the power of negative activation energy over RT. T is the temperature, E sub A is the activation energy, R is the ideal gas constant. So we need this factor in the reaction rate. The second one is the probability of the particle colliding at the right angle, and it's the so-called orientation factor. And this orientation factor is denoted by F. F is unitless, and it's often much smaller than 1. Loosely speaking, F includes the entropic effect, so we often call that entropy factor as well. We have the energy factor, we have the entropy factor. Now, including both the energy and the orientation factor, we have this expression. We have F as the orientation factor, e to the power of negative activation energy over RT as the energy factor. Uppercase Z12 is the collisional frequency between all type 1 and all type 2 particles per unit volume, and that's the reaction rate. I just somehow expanded this Z12 as the average relative speed times the collisional cross-section area times the number densities of type 1 and type 2. We can also express this number density in terms of concentration. So this N1 over V is the lowercase n1 over V times Avogadro constant. That's just the concentration of type 1 times Avogadro constant. In kinetics, we sometimes write concentration this way. This is the concentration of type 1 multiplied by Avogadro constant. Similarly, N2 over V, the number density for type 2, is the concentration of type 2 multiplied by Avogadro constant. So we can rewrite this equation for reaction rate. This is the concentration of 1 times Avogadro constant. This is the concentration of 2 times the Avogadro constant. And that's why we have another expression over here, F. I copied F, the exponential function here, the relative speed here, the collisional cross-section area here. The number density is the concentration of 1 times Avogadro constant. The number density of type 2 is the concentration of type 2 times Avogadro constant. Again, the collisional theory allows us to predict the reaction rate between type 1 particles and type 2 particles. Its reaction rate equals the orientation factor, the energy factor, and then the collisional frequency per unit volume. And it can be expanded this way. Now, for elementary bimolecular reactions between type 1 and type 2, we learned another expression for the reaction rate. R, the reaction rate, is simply K times the concentration of 1 and the concentration of type 2. So this is a simple equation we have learned in general chemistry. K is the rate constant. Using Arrhenius equation, K is A, the pre-exponential factor, times the energy factor, e to the power of negative activation energy over RT. So the reaction rate is simply the pre-exponential factor in the rate constant multiplied by this energy factor, all right, in the form of an exponential function times the concentration of 1 times the concentration of 2. And look, we have two equations for a reaction rate. Over here, that's from collisional theory, and over here from general chemistry. I will just put an equal sign between this and this. So over here we have the reaction for reaction rate. On the left, orientation factor, energy factor, average relative speed, collisional cross-section area, concentrations of 1 and 2, Avogadro constant squared. On the right hand side, the pre-exponential factor, the energy factor, the concentrations of 1 and 2. Of course, we can just cancel the exponential function left and right, the concentrations of 1 and 2 left and right, and now we obtain the pre-exponential factor A. It's the orientation factor times the average relative speed times the collisional cross-section area pi d squared multiplied by the Avogadro constant squared. So A is proportional to F, it's proportional to the relative speed, it's proportional to the collisional cross-section area. So A implicitly includes the entropic effect that's embedded in this F, the orientation factor. Chapter 11, Kinetic Theory of Gases, Section 11.5, Mean free path. The mean free path is defined as the average distance a gas particle travels between two successive collisions. It's denoted by a Greek letter lambda. Now let's look at this graph to see how we can determine the value of lambda. So this red sphere is colliding with this green sphere, changes its direction, collide to the second green sphere, the third one, the fourth one, and the fifth one. And now this mean free path is just the average of lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5. And over here we have an equation, the sum of all those segments divided by the number of segments. And also you can see the number of segments is equal to the number of collisions. 1 collision, 2, 3, 4, 5. 5 collisions, 5 segments. So really the average distance is the total distance divided by the number of collisions. The total distance is the sum of all those lambdas. 5 of them, we sum it up and divide it by 5. But if we are looking at a certain time period, then lambda is simply the total distance this particle has traveled within time interval delta t. On top, on the bottom is the number of collisions in delta t. And again, the number of collisions in delta t is equal to the number of segments over here. You can see 5 collisions, 5 segments. Now on top, it's just the average speed of this particle times delta t. On the bottom, it's the collisional frequency of the particle multiplied by delta t. Delta t and delta t cancel. On top, we have the average speed of this particle. On the bottom, we have the relative average speed. So over here, when we derive the collision between two type 1 particles, we need to use this v sub 11 here. That means the relative average speed between type 1 and type 1. Sigma is the collisional cross-section area. N1 over V is the number density. So we have this equation in the end, because the average relative speed is the square root of 2 times the average speed. So we have this equation. We can further express this equation in terms of pressure and temperature, because very often the temperature and pressure are given. So lambda is equal to 1 over the square root of 2 times sigma, the collisional cross-section area. And over here we simply express the number of particles as the number of moles times the Avogadro constant. We rearrange this equation, we see V over N1 on top. Well, using ideal gas law, it's just RT over P. So we get this expression. And this expression is equal to this expression because R over NA is the Boltzmann constant. So in the end, it can be just the Boltzmann constant times temperature divided by the square root of 2 divided by sigma and P. The mean free path is inversely proportional to the collisional cross-section area, sigma. It's understandable because if you have larger particles, you have more frequent collisions, and that will make the lambda smaller. It's also proportional to the molar volume of the gas. Over here you can see the molar volume, because if you have a larger molar volume, it's hard for a particle to find another particle. It has to travel a longer distance to encounter another particle. If temperature is held constant, then lambda is inversely proportional to pressure over here. But if pressure is constant, then lambda is just proportional to the temperature. So either way, you can express lambda as a function of molar volume or as a function of temperature and pressure. Depending on what information is given to us, we can use any one of those equations. They are all correct. They are equivalent to each other. Now let's look at one numerical example problem, 11.5.1. Let's calculate the mean free path of argon. Sigma is given. This is the collisional cross-section area, 0.36 nanometer squared. By looking at this, you can probably understand the radius of argon can be computed by pi r squared equals this, roughly. Now we're given pressure and temperature. Let's calculate the mean free path. So in the previous slide we have a bunch of equations, but since temperature and pressure are given, we'll just use this equation. We have Kb on top, T on top. On the bottom we have pressure here. We have sigma in meters squared because we want to use SI units. The result is 80 nanometers. So on average, between two successive collisions, an argon atom has to travel about 80 nanometers. What if we have a lower pressure? Let's keep the temperature constant, drop the pressure to 0.1 atm, and you can see lambda becomes 800 nanometers. Well, it's just because lambda is inversely proportional to pressure when temperature is held constant. Now let's look at example problem 11.5.2. We're calculating the mean free path of helium with a smaller collisional section area at 1 atm and 298 K. So same equation, 130 nanometers. We can compare this to numerical examples. Over here we have a smaller collisional cross-section area. That makes it hard for the helium to collide with another helium. It's a little bit harder than this. Alright, just imagine in a room you have blindfolded birds flying around. If the birds are really big, they will collide very often. But if the birds are very tiny, like hummingbirds, so even if they just fly in random directions, it's hard for them to collide with each other, only because the sizes are small. Their collisional cross-sectional area is small. So that's why we have a longer mean free path. So again, just by looking at the equation, you can see lambda is inversely proportional to the collisional cross-section area. Again, just to emphasize, this lambda is proportional to the molar volume. If you have a larger volume, that means the particles are further away from each other, and then you of course will have a larger lambda. If the molar volume approaches infinity, well, then lambda approaches infinity. Chapter 11, Kinetic Theory of Gases, Section 11.6, Mass Transport and Thermal Conduction. Diffusion and effusion are two types of mass transport processes. Effusion is the process in which gas particles pass through a tiny hole of a container. Gas effusion can be used to produce a beam of gas particles. For example, molecular beams. The effusion rate is proportional to the average speed of the gas particles and also the size of the hole. Let's watch a video on effusion.
Effusion is the process of gaseous atoms flowing into a vacuum through a hole in a container.
As you can see, if the gas particles move faster, we'll have a higher effusion rate. And also, if the size of the hole is slightly larger, that means, well, it's easier for those particles to pass through, and we'll also have a higher effusion rate. Now let's talk about diffusion. Diffusion is the process by which particle density evolves in response to a spatial gradient in concentration. Well, let's look at this diagram. Over here we have only one particle. At first there was a partition. This particle can only move in this area. If we remove the partition, this particle can reach to the other area here. Now let's look at a bunch of particles. Again, at the beginning we have a partition over here. We have all those particles in the left side area, and then after we remove the partition, the particles can occupy the entire space. And this is actually diffusion, because at the beginning we have a high concentration on the left, a zero concentration on the right, and just due to the random motions of the gas particles, eventually they will occupy the entire container. The concentration will be homogeneous in the end. And over here we see a kind of more continuous spectrum of the number density. At the beginning we have a high density on the left, and gradually it diffuses to the right. In the end, the color is homogeneous, and that's a so-called equilibrium regarding the concentrations. The diffusion rate is also proportional to the average speed of the molecules, so if they move faster, they can occupy the entire container first. And also it's proportional to the concentration gradient. So what does that mean? So if there's a zero concentration gradient, like right now, okay, there's no more diffusion. The net diffusion rate is going to be zero. If you have a container with a homogeneous concentration inside. Now let's watch a video on the diffusion of ammonia and also HCl. So you can see over here in this picture, ammonia travels a longer distance than HCl. And why is that? Well, the molar mass of ammonia is 17. The molar mass of HCl is about 36.5. So ammonia has a much smaller molar mass and therefore higher average speed. The average speed is proportional to the square root of 1 over m, where m is the mass of the gas particle. So since ammonia is much lighter than HCl, it travels faster than HCl. Now let's watch the video. So over here you see ammonia and HCl diffuse.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two
they form ammonium chloride over here. So by doing this experiments, we can actually just measure the ratio between the average speed of ammonia and the average speed of HCl. So it's going to be just this distance divided by this distance. And that's one way to study the kinetic theory of gases. The diffusion rate is proportional to the concentration gradient and also the average speed of the molecules. So we will study the diffusion rate and how it depends on the concentration gradient and average speed more quantitatively on this slide. Assuming a gas diffuses in the x direction, so this is going to be x, and we're going to see some net diffusion from left to right. At the end, we should have a homogeneous concentration distribution like this. Alright, but at first, let's assume we have a concentration gradient, we have a lower concentration on the left, we have a higher concentration on the right. Let's derive the net diffusion rate at the position x. We will just examine the flow rate of the gas particles in the forward direction and also in the backward direction, and we'll take the difference. That's going to be the diffusion rate. We'll assume the number density at position x is rho. So over here the number density is rho. Now we're going to assume the gradient of the number density is a constant. We're going to use g for that gradient, which is d rho over dx. And therefore, the number density at over here, x minus dx, it's going to be rho minus g dx. The number density at x plus dx is going to be rho plus g dx. Alright, so we have different density on the left and on the right. Okay, over here, this graph is a bit exaggeration. Alright, so you can see the density here is much smaller than the density here. The average number density between x minus dx and x, so between here and here, I'm going to take the average. So it's going to be rho here and rho minus g dx here, so I'm going to take the average. On average, the density here is rho minus g dx over 2. What about the average density over here? Again, I'm going to take the average between over here, it's rho, over here it's rho plus g dx. The average is rho plus g dx over 2. So we have a concentration gradient. The concentration on the left is lower than on the right. On the left, the average is rho minus g dx over 2. On the right, it's rho plus g dx over 2. And then we can compute the number of particles between x minus dx and x. Well, it's just the number density multiplied by the volume. The volume is just the this distance multiplied by the surface area. I'm going to just use A here. Don't worry about the value of A. It's going to be the same for the left side and for the right side. Eventually, they will just cancel. So we have this number of particles on the left. Similarly, we have the number of particles on the right. These two have the almost the same expression, except we have a minus here and a plus here. For simplicity, we're going to assume half of the molecules moving forward, half moving backward, or at an average speed v. So within a time interval, dt as dx over v, then the number of particles moving forward and crossing x is this much. So it's going to be 1/2. It's just because we're going to assume just 1/2 of the particles are moving forward and cross the midpoint. Alright, just 1/2. This is just the volume of the left side, and this is the number density of the left side. The number of particles moving backward and crossing the midpoint is 1/2 times the volume of the right side times the number density of the right side. So we have this number of particles that move forward and backward and cross the midpoint. So I want to show you the diagram again. So we have half of the molecules moving forward and passing the midpoint. Also, we have the expression for the number of particles moving backward and cross the midpoint. Alright, now the overall particle flow rate due to the concentration gradient, well, it's going to be this. This is moving forward, this is moving backward, and then we have over here, this is just the time interval, and we're going to divide everything by the unit volume. So we have this so-called overall particle flow rate due to the concentration gradient per unit volume. Alright, so we have this fairly complicated equation, but on top, this is the number of particles moving forward minus the number of particles moving backward. Alright, just so that we have a net flow rate. Okay, this is just the time interval, and over here it's just we just want to know what's the flow rate per unit volume. And now we have equations to simplify. I see ADX, ADX, ADX. Let's cancel all of them. We have time interval on the bottom. We just copy that. And then we have something over here. DX, 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 they cancel. And also rho and rho cancel. And then in the end, we get negative GV over 2. Alright, G is the gradient of the number density. So you can see this diffusion rate is proportional to the gradient. And the V is the average speed. Now you can see the diffusion rate is also proportional to V. Why do we have a negative sign? Well, it's just because the direction of the flow is from higher concentration area to the lower concentration area. Alright, that's why we have a negative sign over there. So this gradient is positive from lower concentrated region to a higher concentrated region, but the diffusion is from higher concentration to lower concentration. Although this derivation, this entire derivation is not really rigorous, but at least we just proved semi-quantitatively that the diffusion rate is proportional to the concentration gradient, and also proportional to the average speed of the gas particles. For comparison, the diffusion rate mainly depends on 1. The speed of the particles, and 2. The size of the aperture through which the gas particles pass. Now let's look at thermal conduction. Thermal conduction and the diffusion of gas particles are similar, and they are both considered energy dispersal processes, and they both increase the entropy of the universe. As the diffusion rate is proportional to the concentration gradient, the thermal conduction or heat transfer rate is proportional to the temperature gradient. Of course, if the temperature is the same everywhere, there's no more thermal conduction. As the diffusion rate is proportional to the average speed of the gas particles, that is how fast the particles move, the thermal conduction rate depends on the thermal conductivity of the material. So that means how fast the thermal energy can be transferred. Usually metals have higher thermal conductivity than non-metal. In essence, thermal conduction results in the redistribution of the thermal energy of particles, while diffusion results in the redistribution of the positions of the particles. As the positions of the particles are redistributed in diffusion, the energy possessed by those particles are consequently redistributed. Therefore, it's also considered as energy dispersal. So both diffusion and thermal conduction involve energy dispersal. That means energy always flows spontaneously from a high energy density area to a low energy density area. This is dictated by the second law of thermodynamics. Over here, there's animation of thermal conduction. We have a high temperature region and low temperature region, and you can see heat is transferred from left to right. Chapter 12, Elementary Chemical Kinetics. Section 12.1, Elementary reactions versus reaction mechanisms. Chemical kinetics is the study of the chemical reaction rates and the mechanisms of chemical reactions. A chemical reaction may proceed in one step, so-called elementary step, or multiple steps, which constitute a complex mechanism. For example, this reaction between hydrogen and fluorine in the gas phase is likely an elementary reaction. So this hydrogen may attack one of the two fluorine atoms and form a transition state with a partial bond between the hydrogen and the fluorine. And also, this fluorine-fluorine bond is partially broken, and therefore we have a transition state structure with two partial bonds. And this structure resembles something between the reactant and the product. In the product, you have a hydrogen-fluorine bond. In the reactant, you have fluorine-fluorine bond. And in the transition state structure, you have two partial bonds. Well, another similarly simple reaction, the combustion of methane in oxygen, is a complex chemical mechanism. It consists of multiple elementary steps. So this reaction, looks easy, but there's no way for this reaction to proceed in only one elementary step. It is not always easy to tell if a reaction is an elementary reaction or consists of multiple steps. But an elementary reaction often has the following characteristics, with some exceptions. Number one, no more than two bonds are broken in an elementary reaction. No more than two new bonds are formed in an elementary reaction. It is rare to have three or more bonds broken or three or more bonds formed in an elementary reaction, except for concerted reactions, such as the Diels order reaction. Number two, it's often straightforward to draw the transition state structure of an elementary reaction by replacing the breaking bonds with partial bonds and the forming bonds also with partial bonds. For example, in this transition state for this reaction between hydrogen and fluorine 2, the FF bond is partially broken in the transition state. The hydrogen-fluorine bond is partially formed in this transition state. Conversely, it's impossible to draw the transition state for a reaction like this, the combustion of methane. You can try it, but in this, if there were a transition state, you'll have to have, for example, 4 partial bonds between the carbon and 4 hydrogen atoms. And you need to have some partial bonds over here. And in the end, you need to have partial bonds between carbon and oxygen, and also some partial bonds between oxygen and hydrogen. I don't think it's possible to draw any transition state structure for this reaction. Therefore, this reaction must be a complex mechanism. For this order reaction, although I think we will have to sometimes break 3 plus bonds and form 3 new bonds. For example, if you have 1,3-butadiene reacting with ethylene, and in the transition state you have 6 partial bonds. 3 are considered partially broken, 3 are partially formed, but it's also straightforward to draw the transition state structure for the Diels order reaction. So the Diels order reaction is a elementary step. Now let's examine the combustion of methane in oxygen in more detail. In this reaction, we need to break 4 carbon-hydrogen bonds. We need to completely break 2 oxygen-oxygen double bonds, and we need to form 2 new carbon-oxygen double bonds and 4 OH bonds in this 2 water molecules. So again, it's just impossible to draw a single transition state structure, with all those partial bonds, and therefore this reaction, the combustion of methane and oxygen, just cannot be an elementary reaction. We can look at the simplified mechanism of this reaction. It not only involves multiple steps, but also multiple stages. First stage is initiation. We can produce some radicals, such as methyl radical, hydrogen radical, oxygen radical. And in this initiation stage, a lot of energy is required to overcome the barrier, because right here we're breaking a carbon-hydrogen bond, here we're breaking the oxygen-oxygen double bond. There are some branching reactions. So over here, this hydrogen radical can attack oxygen 2 molecule to form 2 radicals, hydroxide and oxygen radical. There is also propagation stage. Over here I listed the 9 elementary reactions. For example, a hydrogen radical may attack a methane molecule and form a methyl radical and H2. The methyl radical may react with a oxygen atom to form this is formaldehyde plus a hydrogen radical, etc., etc. So there are many reactions, elementary reactions in this propagation category. Also, there's a termination stage, because in the end, after the combustion is complete, the radicals actually can undergo those recombination reactions. So these 2 radicals may form a bond, and then we have a molecule with all electrons being paired. And in this reaction, very likely energy will be released, and this energy has to be taken away by something else. Otherwise, this product is not going to be stable. So we use M to denote some medium molecules that can take away the energy from the recombination reactions between the radicals. M star denotes the energized medium molecules. So M absorbs some energy released from this recombination of radicals, and becomes M star. And in this chemical reaction mechanism, very likely the initiation stage is the rate limiting stage. So very likely these 2 reactions might be the rate limiting steps. And I think it's gonna take more energy to break a oxygen double bond. So very likely all this reactions starts with the carbon-hydrogen bond breaking. So approximately, I think the energy barrier is just the energy barrier of this reaction, or the bond energy between carbon and hydrogen. Well, that's why if you just mix methane and oxygen, nothing will happen. You do need to ignite the reaction mixture. That means to provide energy to break at least one carbon-hydrogen bond. Once you have these two radicals, well, you can initiate many other propagation reactions or branching reactions. We talked about the difference between elementary reactions versus reaction mechanisms. But a chemical reaction may proceed in two or more reaction pathways. And it is possible that one of the pathways is elementary reaction, and the others are complex mechanisms. For example, let's look at this reaction. H2 plus F2. We can form 2 hydrogen fluoride, and it can involve different reaction pathways. So first, let's look at one complex mechanism that involve multiple elementary steps. Step 1, we can break a fluorine-fluorine bond to generate a fluorine radical. So this is considered initiation. And then propagation, fluorine can react with H2 to form hydrogen fluoride and H radical. H radical can react with fluorine 2 to form hydrogen fluoride and F radical. And then this F radical can react with H2 again. So we have this two propagation reactions going on. In the end, the hydrogen radical and the fluorine radical form a bond, and we get hydrogen fluoride. Energy is released, and the released energy must be absorbed by some medium molecules, and that's why we need this M over here, and this M is energized after absorbing the energy and become M star. M star means energized medium molecules. Sometimes we can just use argon gas as the medium. Sometimes we can use some other inert chemicals as the medium for this reaction. This is the complex mechanism for this reaction. We can also make another conjecture that H2 and F2 may react in a different pathway that involves only one single elementary step. In this step, we have a four-centered transition state structure. So over here, this is the structure. We have 4 partial bonds. Hydrogen-hydrogen bond is partially broken. So is the FF bond, and then we have 2 partially formed hydrogen-fluorine bonds in a transition state. How do we know which mechanism is the predominant mechanism? So which one is the predominant pathway? Well, we'll have to do some quantum mechanical calculations. We can compute the energy barrier for this mechanism versus the energy barrier for this elementary reaction. Alright, whichever has a lower barrier is going to be faster, or considered as the predominant pathway. And we consider this like parallel mechanism because it's possible for H2 and F2 reacting in this described by this mechanism. Also, it's possible for H2 and fluorine 2 reacting described by this transition state. So both pathways are possible, and when there are multiple pathways in parallel, that means they take place at the same time, then the fastest pathway is the predominant reaction pathway. Chapter 12, Elementary Chemical Kinetics. Section 12.2, Reaction Rates. It is straightforward to define the reaction rate for elementary reactions. The reaction rate is denoted by R, and R can be the consumption rate of the reactants. R can be the production rate of the products. Here's one example: hydrogen atoms. react with fluorine gas to produce hydrogen fluoride and fluorine atoms. How do we define the reaction rate? Well, the reaction rate R can be how fast the hydrogen atoms are consumed, or how fast the fluorine molecule is consumed, or how fast hydrogen fluoride is produced, or how fast the fluorine atoms are produced. For this kind of reaction with different coefficients, we'll have to be a little careful here, because the production rate of the fluorine atoms is 2 times the consumption rate of the F2 molecule, and therefore the reaction rate may be defined as this way. It's how fast F2 is consumed, or how fast the fluorine atoms are produced, divided by 2. Again, it's just due to the difference in the stoichiometric coefficients. For complex mechanisms, the ratio between stoichiometric coefficients do not always reflect the instantaneous ratio between the consumption or production rate, but over a long enough reaction period they do, approximately. For example, if we look at the combustion of methane in oxygen, well, we cannot easily define the instantaneous reaction rate. It's just because when CH4 is consumed, we're not really getting one CO2 or one water. Very likely at the beginning of the reaction, when one CH4 molecule is consumed, we actually have a methyl radical and one hydrogen atom being produced. So it's not going to reflect the change of O2 or CO2 or water. However, when the reaction is complete or nearly complete, we can look at the stoichiometric coefficients. And now the reaction rate can be defined as the production rate of CO2 or the production rate of water divided by 2 due to this coefficient. It can be the consumption rate of CH4 or the consumption rate of O2 divided by 2. Again, those stoichiometric coefficients should be used in the expression of reaction rate, and we should use their reciprocals. Again, for example, if let's say 1 mole CO2 is produced, then at the same time 2 moles of water are produced. Therefore, we need to divide the production rate of water by 2 so that this equal sign holds. For convenience, the unit for reaction rate is the unit of concentration divided by the unit of time. This is because concentration is an intensive property, while the amount or the number of moles of a chemical is an extensive property. It's impossible to enumerate all possible values of any extensive property when we are trying to describe how fast a reaction goes. So for example, if you have hydrogen reacting with a fluorine atom to produce hydrogen fluoride and a hydrogen radical, how fast this reaction proceeds? Well, if you use the number of moles per unit time, well, then you have to specify the amount of all chemicals. It's an extensive property. It can hardly be tabulated with all possible values. That's why we often use the concentrations and their changes over time to describe the reaction rates. When we use the changes of concentration per unit time as the reaction rate, we often use a non-SI unit in chemical kinetics. It's molar per second. Molar is a non-SI unit. Molar is mole per liter. Mole is the SI unit for the amount, but liter is not. Liter is 10 to the power of negative 3 cubic meter, while cubic meter is the SI unit for volume. But still, for convenience, we often use molar per second as the unit for the reaction rate. The reason we do not like to use mole per second is this. A reaction in a 1 liter container versus the same reaction in a 5,000 liter container. They may have the same reaction rate expressed in molar per second, but their reaction rates may differ by a factor of 5,000. If the reaction rate were expressed in the units of mole per second. So that's why it's more convenient to use molar per second than mole per second. There are many other units for reaction rate. Another commonly used non-SI unit of reaction rate is molecule per cubic centimeter per second. We can do some derivations to connect this unit to this unit. 1 molar per second is 1 mole per liter per second, and 1 liter is 1,000 cubic centimeter, and 1 mole is 6 times 10 to the power of 23 molecules. Therefore, over here we have 1 molar per second is 6 times 10 to the power of 20 molecules per cubic centimeter per second. When reactions are really slow, we tend to use this unit of molecule per cubic centimeter per second. When the reaction rate is faster or much faster, we tend to use molar per second. Again, for extremely slow reactions, we use this molecule per cubic centimeter per second just for convenience. The SI unit for reaction rate is mole per cubic meter per second, but this is rarely used in chemical kinetics. We can do some conversion here. So 1 molar per second is 1 mole per liter per second, which is 1 mole per 0.001 cubic meter per second, and it's 1,000 mole per cubic meter per second. Also, we can convert this to molecule per cubic centimeter per second. The derivation is straightforward. Chapter 12, Elementary Chemical Kinetics, Section 12.3, Rate Loss and Integrated Rate Loss. We will study the rate loss and the integrated rate loss for the 0th, 1st, and 2nd order elementary reactions in this section. For the 0th reaction, the reaction rate is a constant. From A to P, if it's a 0th order reaction, the reaction rate R is equal to the rate constant K multiplied by A to the power of 0. Therefore, it's called a 0th order. And really, R is equal to K. K is the reaction rate constant. It's also known as reaction rate coefficient. For the 1st order reaction, the reaction rate is proportional to the concentration of the reactant to the power of 1. So from A to P, if it's a 1st order reaction, R is K times A to the power of 1. Now if we have 2A to P, if it's second order, then the reaction rate is proportional to the concentration of the reactant to the power of 2. The reaction rate is the rate constant K times A to the power of 2, and thus second order. We have another type of second order reactions from A plus B to P. It is possible for the reaction rate to be proportional to A to the power of 1 and also to B to the power of 1. Written in this equation, R is K times the concentration of A times the concentration of B. The reaction order is 1 with respect to A, it's 1 with respect to B, but overall the reaction is second order. 1 plus 1 is 2. Third order elementary reactions are extremely slow because the chance of 3 reactant molecules colliding at the same position and with the right angles of collision is slim. The unit of the reaction rate R is always the unit of concentration divided by the unit of time, because R is how fast the concentration of reactants or products change with time. We often use molar per second for the units of the reaction rate. The unit of rate constant K, however, may vary. In general, the unit of K, the rate constant, is molar to the power of 1 minus n divided by second, and n is the overall reaction order. So if n is 0, we have a zeroth order reaction, and then the unit of K is just molar per second, the same as the reaction rate R. If we have a first order reaction, n is 1, the unit of K is simply second to the power of -1. When n is 2, the unit of K is m to the power of -1, second to the power of -1. Well, this is just because K is equal to the reaction rate over the reactant to the power of n for nth order reaction. This results in the unit of K being molar to the power of 1 minus n, second to the power of -1. So we tabulate the unit of R and unit of K for the 0th, first, and second order reactions. If we look at the unit of R, it's always molar per second. This is just how fast the concentrations of the reactants or products change with time. So they have just the same constant unit as concentration over time. What about the unit of K? Well, again, the unit of K really depends on this reaction order. If it's 0th order, R equals K. If it's the first order, R equals K times concentration of A. Therefore, we have the unit of K as second to the power of -1. Now, in this case, for the second order, R is K times A squared, and therefore R and K should differ by A squared. The units differ by m to the power of 2. Same here for the second type of second order reaction from A plus B to P. R is K times the concentration of A, and then times the concentration of B. And therefore, the unit of K should be molar to the power of -1, second to the power of -1. What if you have a third order reaction such as 3A to P, 2A plus B to P, or A plus B plus C to P? This kind of elementary reactions, the unit of K is molar to the power of -2, second power to the power of -1. We just use the same formula over here. Fourth order reactions, well, molar to the power of -3, second to the power of -1. Honestly, I have never seen any fourth order reactions myself, including textbooks or scientific papers. Given the reaction rate R at various concentrations of the reactants, we can determine the order of the reaction rate with respect to each reactant. For example, if a reaction involves two reactants denoted by A and B, we may simply just assume R is K to the power of A to the power of alpha, B to the power of beta. Alpha and beta are the orders of the reaction with respect to A and B. And we can determine the values of alpha and beta. If you have an elementary reaction, alpha and beta are simply the coefficients in front of A and B in a balanced chemical reaction. But if you have a complex reaction mechanism, alpha and beta are not necessarily the coefficients of A and B. Alpha and beta are not necessarily integers. And sometimes we can even have a different form than this. So R is a more complex function of the concentrations of alpha and beta. But now let's just assume this equation is sufficient to describe the mechanisms, and then we can just take the natural logarithm of this equation. We get the natural logarithm of R is equal to logarithm of K plus alpha times the logarithm of A plus beta times the logarithm of B. If B is held constant, then we have L1R versus L1A graph with a slope of alpha. So again, if B is constant, we can view L1K plus beta L1B, these two together, as the intercept. When we plot L1R versus L1A, the alpha is simply the slope. Now what if we hold A constant? Now L1K plus A L1A, these two terms together are considered the intercept of the L1R versus L1B plot, and beta is the slope. Well, we can also just determine alpha and beta without plotting L1R versus L1A or L1R versus L1B. Well, it's simply because if B is held constant, if we have the value of the reaction rate at two different concentrations of A, we can do this. Alpha is the change of L1A over the change of L1A. On top it's L1R. Well, why is this? If you look at this, basically it's the slope of L1R versus L1A. And then we just plug in the values. What's the change of L1R? What's the change of L1A? The change of L1R is L1R2 over R1. The change of A is L1A2 minus divided by A1. So we have this. Again, if we hold B constant and can measure the reaction rate for two different concentrations of A, and then we can plug in these four values to get alpha. For example, if the reaction rate doubles, when A doubles, we simply have this equal to 2, this equal to 2, the alpha is just 1. Alright, so two different ways. One is you can just plot L1R versus L1A. You determine the slope is alpha, or you can just do algebraic operations like this. You will determine alpha by hand. Again, if there are two reactants, we can just assume The reaction rate is often K times A to the power of alpha, B to the power of beta. And we take the natural logarithms of both sides. We get ln R equals ln K plus alpha ln A plus beta ln B. Now if A is held constant, again we can hand calculate the value of beta. It's the change of ln R over the change of ln B. The physical meaning of this is just the slope of ln R versus ln B. That's just the slope. But again, we can do the hand calculations as well if you know the values of the reaction rate constants at two different concentrations of B. We plug in all the numbers, we get beta. For example, if the reaction rate quadruples when B is doubled, then B2 over B1 is 2, R2 over R1 is 4. Plugging all those values, beta equals 2. The overall order of this reaction is alpha plus beta. And also, if we have the values of the reaction rate at three different combinations of concentrations of A and B, we can then write out three equations. And these three are linear equations. They contain three variables: K, the rate constants, alpha, and beta. We just need to plug in the values of R at different concentrations of A and B, and then we have three linear equations that contain three variables. In principle, we can solve the three equations and get the values of K, the rate constant, alpha and beta, the reaction orders, with respect to A and B. Now let's examine the zeroth order, first order, and second order reactions and derive their integrated rate laws. For the zeroth order reaction from A to P, the reaction rate is constant. R is simply equal to K, or K times A to the power of 0. Either way, K is the reaction rate constant. Sometimes it's called a reaction rate coefficient because scientists feel like this K may change with temperature. So maybe coefficient is a better naming for K. Now R is often defined to be dP over dt, how fast P is produced, or how fast the concentration of P changes with time. And looking at these two equations, we know dP over dt is K, so dP is K dt. We integrate both sides, and then we have P equals P naught plus KT. P naught is simply just P at time 0, so you can verify this equation. You plug in time equals 0, you get P equals P naught. That's it. Very often P naught is 0. You know, why would we have any product at the beginning of the reaction unless you put some product in the reaction system? And that's rare, so very often we have just P equals KT. But this is kind of more general equation. Now let's look at one numerical example problem, 12.3.1, in a zeroth order reaction. The concentration of the product is 0.065 molar at 1 minute, 0.095 minute at 2 minutes. Determine the rate constant K and also P naught. So we have this equation. We plug in all the values. We solve this equation. We get K is 0.03 molar per minute. Well, it's really simple. You just take difference between these two equations. You'll get K. And then you plug in the value of K, you get P naught, which is 0.035 molar. So that means at the beginning of this reaction, we have some P already in the system. Its concentration is 0.035 molar. If we plot P versus time for the zeroth order reaction, it's just linear. And over here, the intercept is the initial concentration of the product. Well, usually this is 0. The slope is just a constant k at a given temperature. For the zeros order reaction from A to P, the reaction rate is constant. We have P equals P naught plus KT. So we can make a graph of P versus time. The intercept is P naught, the slope is K. So we can always make a plot like this to determine the value of K if we have more than 2 data points. If we have only 2 data points, I'd rather just solve 2 linear equations. Again, if P naught is 0, then P is equal to KT. And this is actually more common. Why would a reaction be a 0th order reaction? Why does the reaction rate R not depend on the concentration of the reactants? There are 3 possible reasons. One is we do have a reactant A, it's constantly consumed, but it's also constantly replenished, so that A never changes. A is kept constant. Alright, so there's one way to do it. Reason number 2, A is a pure liquid or pure solid, so the concentration of A is constant. For example, if the reactant is just pure water, pure water has a constant concentration in molar or mole or mole fraction. If you look at the mole fraction of pure water, it's always 1, so it never changes. Reason number 3, A decreases as the reaction proceeds, okay, but R does not depend on A. For example, if we have a reaction that's induced by photons, and only if A absorbs a photon, a reaction can take place, and we have fewer photons than the number of A's, and then the reaction rate solely depends on the number of photons provided to the system per unit time, right? So if you have, for example, a bunch of A but only 1 photon per hour, then the reaction rate is just 1 molecule of A converted per hour. It has nothing to do with the concentration of A anymore. It's limited by the number of photons provided to the system per unit time. Because A may be constant as the reaction proceeds, we don't usually like to use this equation to define the reaction rate R. What if A is always replenished, A is a pure liquid, and then dA is just 0, then R is 0, and that's not true. So very often we do not use this equation for the reaction rate. Instead, we say the reaction rate is equal to dP over dt for the 0th order reactions. For the 1st order elementary reaction from A to P, R is K times A to the power 1. And now we can write the reaction rate as the consumption rate of A or the production rate of P at the same time. We have 3 equal signs, but we will use this equation to solve for the integrated law of the 1st order reactions, because if we look at this equation, there are only 2 variables, A changes, T changes. K is constant at a given temperature. So how do we solve this? First, we rearrange the variables. So A appears on one side of the equation, T appears on the other side. The separation of variables is very important. We do that first so that we can integrate both sides. Again, if you have 2 variables on the same side of the equation, you cannot easily integrate that side. You want to have only 1 variable on each side of the equation before you integrate both sides. The integral of dA over A is L1A, the integral of negative k dt is negative kt, and because we're doing indefinite integrals without lower and upper limits, we need to plus a constant. We can determine the constant C given the initial condition, If A is A naught when time is 0, and A naught denotes A at time 0, then we plug in those expressions. We replace A with A naught and T with 0, and you can see this constant C over here in this equation is simply ln A naught. Therefore, ln A is negative kt plus ln A naught. Equivalently, A is A naught times exponential function. This exponential function is e to the power of negative kt. And now, if you just look at these two equations, we can use either one to analyze this concentration change of A. If we use the logarithm equation, we can make a graph of ln A versus time. You can see the slope should be negative k, the intercept should be ln A naught. So this is one way to determine the reaction rate constant k. Just plot ln A versus t, you get a linear equation, the slope is negative k. And if you have only 2 data points, you can always solve 2 linear equations that contain 2 variables. Alright, so for example, if you know the concentration of A at the beginning and the concentration of A after 1 second, and it's the first order equation, so you can use this, and then you can hand calculate the value of K as well. You can also use this equation if you have the initial concentration of A, alright, and you have this, and at t equals 1 second or 2 minutes, whatever, you have another concentration of A. Plugging all those values, you determine K. So it's possible to hand calculate the value of K. But if you have more than 2 data points, if you have 3 data points, 4 data points at different time, just make a graph, do a linear regression, determine the slope, and remember the slope is negative k. I did use ln A as the vertical axis, but really it should be ln A over molar, just to remove the unit. It's just because the logarithm of a unit makes no sense. What's the logarithm of 1 molar? It just doesn't make any sense to have the logarithm of a unit. What's the logarithm of kilogram? It does not make sense. But just for convenience, I'm just using ln right here. You need to keep in mind that when you do this, you are actually removing the units. Now again, look at the rate expression. It can be the consumption rate of A, it can be the production rate of P. So we have negative dA over dt equals dP over dt. Therefore, the sum of these two should be 0. So we have this equation. That means A plus B never changes. Well, that makes sense because whenever one A molecule is consumed, one P molecule is produced. So A plus P never changes. Therefore, A plus P is always A naught plus P naught, and P is A naught plus P naught minus A. And because A is A naught times e to the power of negative kt, so P is P naught plus A naught times 1 minus e to the power of negative kt. Very often, the initial concentration of P is 0, which is again very common. It's rare for us to put some product in the reaction system in the first place. So usually we have P naught is 0, then P is A naught times 1 minus e to the power of negative kt. Alright, we have the expression for the concentration of P as well, and we can plot how P changes with time. Now let's look at the half-life of A. What's half-life? That's when the concentration of A drops to only 50% of the initial concentration. So based on this definition, the concentration at half-life is just 1/2 of A naught. And it's also equal to A naught times e to the power of negative k times half-life. So this is from the integrated rate law of the first order reaction. Now if we compare these two sides, we know we have this A drops to 1/2 of the initial concentration. This exponential function, e to the power of k times the half-life, should be 1/2. And now you have this equation. And then we solve this equation. Given k, we get half-life. Given half-life, we get k. Here's one numerical example problem. 12.3.2. First order elementary reaction from A to P. The concentration of A is 0.2 molar at 1 minute, 0.14 molar at 2 minutes. Determine the half-life of A and determine the initial concentration of A. So we're going to use this equation, alright? Ln A equals negative kT plus, actually this Ln A naught. But we don't even need to know that equation, because we know negative k is going to be the slope of Ln A versus time. So we have the change of Ln A on top, the change of time on the bottom. We determine negative k, it's this. So k is 0.3567 per minute, or 0.005945 per second. Well, I'm keeping actually one extra 6 figures. I usually do that for intermediate results. Now half-life. Half-life is just Ln2 over k. So plugging all the numbers, half-life is determined to be 116.6 seconds, or 1.943 minutes. Since we have this equation, so again, this C is actually Ln A naught. Now we just need to use this equation. We plug in all the numbers. We can use the data at 1 minute or the data at 2 minutes. It doesn't matter. We just plug in the corresponding concentration of A. 0.14 at 2 minutes, 0.2 at 1 minute. We plug in the K with the right unit. Alright, so we're going to use per minute over here, so 2 minutes over here. We determine the concentration of A naught, which is 0.286 molar. Actually, you can just compare 0.286 and 0.14. Well, you can see roughly 0.14 is 1/2 of the initial concentration, so 2 minutes should be close to the half-life. And yes, 2 minutes is indeed close to the half-life. Now let's look at the second order reaction from 2A to P. First, R is K times A squared. That's the rate law for the second order reactions. We need to determine the integrated rate law in half-life. So we write out the reaction rate as how fast the product changes with time. But look, when one product P is produced, 2A are consumed. So the consumption rate of A is 2 times the production rate of P. So this dA over dt is 2 times this dP over dt. That's why we need to put a 1/2 here to balance this equation. We put a negative sign here because dA over dt is negative. dP over dt is positive. So it makes sense to put a negative sign. Or we can say the absolute value of this. But mathematically, it's better to use the negative sign here. Now we just need to solve this equation. How do we solve this? Again, there are 2 variables. We have the concentration of A. We have time t. Always separate the variables. By doing some simple algebraic operations, we managed to have A on the left hand side, T on the right hand side. And then we can integrate both sides. The integral of the left hand side is 1 over A. The integral of the right side is 2kt. But both are indefinite integrals. So we're going to just write plus C, and C is a constant. We can determine the value of the expression of C. given the initial concentration of A at time 0, you just plug in A being A0 here, T being 0 here, and then we can solve for C. Alright, so what is C? C is simply just 1 over A naught. And therefore we get this equation as the integrated law for the second order reaction from 2A to P. It's 1 over A equals 1 over A naught plus 2kT. By looking at this equation, we know if we plot 1 over A versus time, we'll get a slope, and the slope is 2k. The y-intercept is going to be 1 over A naught. Again, for the second order reaction from 2A to P, the reaction rate is 1/2 of dA over dt, and it's dP over dt. And therefore you can see 1/2 dA over dt plus dP over dt should be 0. Therefore we have this equal to 0, and A over 2 plus P is a constant. It never changes with time. Only because when 2A molecules are consumed, 1P is generated. Right? So we have this equation. A over 2 plus P is equal to its value at the beginning. It never changes. And using this equation, we know P is P naught plus 1/2 of A naught minus A. This is the change of A divided by 2. That will be the change of P. If the initial concentration of P is 0, which is common, P naught is 0, then P is just 1/2 of A naught minus A. The half-life of A can be calculated easily using this equation from the integrated rate law. It's just we need to use the equation for the time right at the half-life of A. Therefore 1 over the concentration of A at half-life is 1 over A naught over 2. That's the definition of half-life. It's equal to 1 over A naught plus 2k times half-life. That's from the integrated rate law. Now we can solve this equation really easily. So we have 2 over A naught, which is from here, minus 1 over A naught is 2k times half-life. It's kind of interesting here. The half-life of the reactant in the second order elementary reaction depends not only on the rate constant but also on the initial concentration of the reactant. Because by looking at this, you know the half-life is 1 over 2k times A naught. It depends on both k and A naught. Recall that for the first order reaction from A to P, the half-life is ln2 over k. The half-life of the first order reaction depends only on the value of the rate constant. But over here, the second order, this half-life depends on both k and A naught. Now let's look at one numerical example problem, 12.3.3. In a second order elementary reaction from 2A to P, we have some data points. A is 0.2 molar at 1 minute, 0.14 molar at 2 minutes. Determine the rate constant, determine the initial concentration of A, and also the half-life of A. We first write out this equation. We realize that if we plot 1 over A versus T, we'll get 2k. So 2k is the slope of 1 over A versus time. So 2k is the change of 1 over A divided by the change of time. We plug in all the values. We get the expression of 2k. 2k is 2.143 molar to the power of -1, minute to the power of -1. And therefore k is 1/2 of this. And then this value divided by 60, we get the value of k in molar -1, second -1. Again, we have this equation. We can just plug in the values of A at 1 minute, So this is concentration of A. This is 1 minute. We solve for A naught. We got A naught equals to 0.35 molar. And how do we get a half-life? Well, the half-life is 1 over 2k A naught. We plug in the value of k, the value of A naught. We get 1.333 minute, 80 seconds. So after 80 seconds, the concentration of A is 1/2 of this, and that's 0.175 molar, which is between these two concentrations given in the question. And also you can see this 80 seconds is between 1 minute and 2 minutes. It's a good way to quickly verify if our answer makes sense. There's another type of second order reactions from A plus B to P. In this case, if A equals B, so if we use the same amount for A and B, then we have this equation. R is K times A times B, but since A equals B, so it's A Ka squared or Kb squared, either way. And the consumption rate is this, and this, and this is the production rate. Note that we do not have 1/2 in front of dA over dt, because look at this coefficient, it's 1-to-1 ratio. And now we just solve this differential equation. It comes from over here, Ka squared equals negative dA over dt, and then we have this equation. We integrate both sides, we get this. 1 over A is 1 over A naught plus KT, and A naught is A at time 0. Alright, we can just easily verify this. We can plug in this expression here, dA over A squared, just to see if it equals kdt, or we'll plug it in here, negative dA over t, right? See if that's K squared. We can verify this equation easily. And now we have this equation. If 1A is consumed, then 1P is produced. So we have this equation. Oh, by the way, if 1A is consumed, at the same time 1B is also consumed, and 1P is produced. So we got this equation, and you can see A plus B never changes. Therefore, A plus P is A naught plus P naught. P naught is often 0. But what if P naught is not 0? Then P is P naught plus A naught minus A. If P naught is 0, then P is A naught minus A. The half-life of A can be calculated using this. Again, this is going to be just 1 over the concentration of A at half-life, which is 1/2 of the initial concentration, which equals this, and then we get the half-life. This half-life is 1 over K A naught. It's a little different from the half-life of A for the second order reaction from 2A to P. So I'm going to show you that half-life. It's 1 over 2K A naught. Here it's 1 over K A naught. Again, it's just because if you look at this equation, 1A, 1P. In the previous equation, it's 2A, 1P. Let's look at a numerical example problem in a second order elementary reaction from A plus B to P. We have concentration of A at 1 minute, and its concentration at 2 minutes. Now this time we're going to solve everything using a slightly different equation. It's just 1 over A equals 1 over A naught plus KT, and K is the slope of 1 over A versus T. So I'm going to use the change of 1 over A on top, the change of T on the bottom. We get the value of K, and we can convert minute to second easily. We write out this equation. Again, we plug in the value of the concentration of A at 1 minute. We can solve for A naught. In this case, A naught is also 0.35 molar. The half-life is 1 over k times a naught, and this time we have 1 over k a naught. It's just the same value, 80 seconds. So in this numerical example, we got the same initial concentration, same half-life, but this k is different. Over here we get k 2.1. I want to show you the previous calculation. This 2k is 2.1. Alright, 1k is 1.07. So the value of k is different between these two examples, but a naught is 0.35 in both examples. Half-life is 80 seconds. Half-life is 80 seconds. Initial concentration is 0.35. For the second order reaction from A plus B to P, it's possible for A to be different from B. That makes the derivation more complicated. We'll just assume B is always A plus delta, because dA over dt equals dB over dt. Given a time period, the change of A should be equal to the change of B. Then we have this equation. That means the change over here of B with respect to time is equal to the change of A with respect to time. Alright, so B minus A never changes. If B minus A never changes, then this delta is a constant. Delta never changes with time. So if at the beginning you have delta equals B naught minus A naught, then throughout the entire reaction, delta is B naught minus A naught. No change. And now R is Ka times B. B is A plus delta. And it's equal to the consumption rate of A or B or the production rate of P. We will solve this equation because it contains only two variables, A and T. We do need to separate the variables again, so we have K times dt equals negative dA over A, and also we have A plus delta on the bottom. How do we integrate this by hand? Well, it's just we can separate this two. We get this expression. So I'll let you verify the left side of the equal sign equals the right side. Alright, we can now integrate both sides. That's easy. Kt is just 1 over delta times the integral of this, which is the logarithm, minus 1 over delta times the logarithm of this, which is normal, which is easy. Got this equation. I did take the initial condition into account, because really if you integrate both sides directly, you're going to get indefinite integrals. But we do know that at time 0, A is A naught. So I'm using this equation to get a definite equation. We can verify this easily. When time is 0, the left side is 0. And when time is 0, A is A naught. A is A naught. The right side is 0. So that's good. Now we have this equation. So again, the difference between two logarithms can be expressed of the logarithm of a division. So over here. And now we can calculate the half-life of A. We just need to replace A with 1/2 of A naught. So that's what I did here. A is 1/2 of A naught. Alright, A is 1/2 of A naught. So this is just 1/2 on the bottom. That means you have a 2 on top. Get this equation, and you simplify everything, you get this equation. The half-life in this case, the half-life of A in this case is just this 1 over delta times Ln A naught plus 2 delta A naught plus delta. What's the half-life of B? Well, it's similar. You just need to replace A naught with B naught. You get the half-life of B. It's really easy. Alright, although it's in the expression of a logarithm of a ratio between A naught plus 2 delta over A naught plus delta. What if a delta approaches 0? how do we deal with this? When delta approaches 0, actually we need to know a little bit about Taylor expansion. So this approaches this. If you know how to do Taylor expansion, the Taylor expansion tells us the logarithm of 1 plus delta is roughly delta, if delta is small. So over here we can see this term is roughly 1 plus, when I say delta, that means a very small number. So not this delta. So the logarithm of, let's say, 1 plus x is approximately x, if x is really small. Alright, if x is really close to 0, let's say if x is 0.01, then the logarithm of 1.01 is roughly 0.001. That's just from the Taylor expansion of the logarithm. Okay, let's get back to this. This part is just 1 plus delta over a naught plus delta. So roughly the logarithm is delta over a naught plus delta. And over here we have 1 over delta. So this whole thing is roughly 1 over a naught plus delta. And this is roughly 1 over a naught. Alright, so when delta approaches 0, we have this equation. And k times half-life is roughly 1 over a naught. And isn't that just the half-life here? The half-life is 1 over ka naught. Get back to this. When delta approaches 0, what's the half-life? Half-life is 1 over k over ka naught. You know, same thing. Alright, when delta approaches 0, we just reduced the more complex situation to over here. I'm sorry, on this page, you know, when a is equal to b, the half-life is 1 over ka naught. And over here, same thing. When delta is approaching 0, k half-life is 1 over a naught. Therefore, half-life is 1 over ka naught. Alright, so in this case, you know, when delta is approaching 0, that means when b is approaching a, the half-life approaches 1 over ka naught. When b is equal to a, the half-life is equal to 1 over ka naught. The last slide of this section, briefly I'll talk about the third order only because I want to show you it's possible to deal with the third order, the fourth order, etc. This is the third order. R is k times a to the power of 3, and it's negative 1/3 dA over dt equals dp over dt. We just solve this differential equation. We separate the variables a on the left hand side, t on the right hand side. We integrate both sides. We get 1 over 2a squared plus 3kt plus a constant. Alright, and then we can determine the expression of the constant because we know at time 0 a is a naught. Plugging a naught here, plugging t is 0 here, c is 1 over 2a naught squared. And now we have the third order rate law, which is 1 over a squared is equal to 6kt plus 1 over a naught squared. We make a graph. It's 1 over a squared. Over here it's t. The slope is 6k. The intercept is 1 over a naught squared. That's it. So given the experimental data, we're just to be able to create a graph and determine the slope. The slope divided by 6 is going to be the rate constant. Also, if you have the concentration of A at 2 different times, plugging those values, we can just solve for K and solve for A naught easily. Chapter 12, Elementary Chemical Kinetics, Section 12.4, Activated Complex Theory. Activated complex theory, also known as transition state theory, states that between the reactants and products in an elementary reaction, there is often a transition state structure. The transition state has a higher energy than both the reactants and the products. The transition state structure resembles something between the reactant and the product. In the transition state structure, one or more bonds in the reactant are partially broken. One or more new bonds in the product are partially formed. Let's look at one example. In this reaction, fluorine reacts with HCl to form a chlorine atom and hydrogen fluoride. And between the reactants and the products, there is a transition state. In the transition state structure, we have fluorine-hydrogen partial bond. We have hydrogen-chlorine partial bond. If we look at this reaction path from left to right, so from the reactants to the transition state, we can see the fluorine-hydrogen partial bond is formed in the transition state. The hydrogen-chlorine bond is now partially broken in the transition state. And finally, in the products, we have a hydrogen-fluorine bond and a individual chlorine atom. Now, what's the difference between the activated complex and a transition state? So right here we see this transition state at the top of the hill right here. But an activated complex may adopt the transition state structure or a structure very close to that of a transition state. So somewhere here, okay, this reactants can form a transition state or something close to that and overcome the barrier to form the products. The activation energy of the reaction is the energy of the transition state minus the energy of the reactants, denoted by E sub A. This is the activation energy. It's the energy of the transition state minus the energy of the reactants. So it simply means the reactants must get some additional energy, this much, to overcome the barrier and form the products. We have the equation over here. Activated complex theory, also known as the transition state theory, states that between the reactants and products in an elementary reaction, there is often a transition state structure that resembles something between the reactant structure and the product structure. Here's another example. Let's look at one of the SN2 reaction. SN stands for nucleophilic substitution. SN2 means it's going to be bimolecular. Now let's look at this reaction. So from chloride and bromomethane to this chloromethane and bromide. In the middle, we have a transition state. So now let's look at the reactants. We have a chloride, we have bromomethane, okay? And let's look at the product. We have a bromide and a chloromethane. So in the middle, we have transition state structure that resembles something in between. Alright, now let's look at over here. The chlorine-carbon bond is now partially formed in the transition state. The carbon-bromine bond is partially broken in the transition state. So that's why you have two partial bonds in the transition state. One is carbon-bromine partial bonds. The other is carbon-chlorine partial bonds. And over here, well, the bond between carbon and bromine is completely broken. The carbon and chlorine bond is completely formed. And now you can see we have energy going up and then going down. This is not the entire potential energy surface for the reaction. You can see on the left hand side we have only 8 data points. On the right hand side we have only 8 data points. So very likely it should extend to like until it levels off, and this one should level off. Alright, and again after it levels off, we'll be able to get the energy of this reactant complex that consists of this bromomethane and chloride, and they should be relatively close to each other, solvated by water molecules. This is the beginning of the reaction, this is the end of the reaction, and this is in the middle between the reactants and the products. Again, the transition state has higher energy than the reactants, but also we need to remember the transition state structure has higher energy than the products. And also, you can view this reaction from right to left. You can go from here. You have bromide reacting with chloromethane, form the transition state structure, and go back to over here with a chloride and bromomethane. In the vertical axis, we have the energy of the three species: reactants, transition state, and product. But those are in a unit of Hartree. One Hartree is 2,600 kilojoule per mole, or 627 kilocal per mole. So even though you can see the energy difference looks small, well, you need to multiply that by 2,600 to convert it to kilojoule per mole. So the energy barrier is not that small. And the horizontal axis is called the intrinsic reaction coordinates. It's just a description about the changes in the structure of from the reactants to the transition state to the product. Chapter 12, Elementary Chemical Kinetics, Section 12.5, the Arrhenius equation and the Irene equation. The Arrhenius equation is an empirical equation proposed by Arrhenius. This equation describes the relation between the reaction rate constant K and temperature T. Although K is called the reaction rate constant, it's not really a constant. K does depend on temperature. As temperature changes, the rate constant changes. Arrhenius proposed that K is equal to A times e to the power of negative activation energy over RT. A is the pre-exponential factor. And then we have exponential function e to the power of negative e sub a over RT, where e sub a is the activation energy. There is also a modified Arrhenius equation. K is a times t to the power of m and times e to the power of negative e prime over RT. It contains one more parameter than the original Arrhenius equation. And usually when we have more parameters in the equation, well, we can use that equation to match with experimental data more accurately. The Irene equation is another equation for computing the reaction rate constant K at different temperatures. The Irene equation is the exact equation of K for first order reactions, assuming the quantum tunneling effect is negligible. We'll talk about quantum tunneling effect in quantum chemistry. So basically, without any quantum tunneling effect for a first order reaction, we can write out the expression for the reaction rate constant K. It's kBT over H times e to the power of negative. Over here we have Gibbs energy of activation over RT. Kb is the Boltzmann constant, H is the Planck constant. And the Gibbs energy of activation is denoted by delta G, double dagger. It's the Gibbs energy of the transition state minus the Gibbs energy of the reactant. At any given temperature T, delta G is delta H minus T delta S. Therefore, the Gibbs energy of activation is equal to the enthalpy of activation minus temperature times the entropy of activation. And therefore, we can rewrite the Irene equation to a function of entropy times a function of enthalpy times, well, a constant. So really, we are just rewriting this delta G double dagger to delta H double dagger minus T delta S double dagger. We have two separate exponential functions. One is e to the power of entropy of activation over R. The other is e to the power of negative enthalpy of activation over RT. The enthalpy and entropy of activation both depend on the reaction temperature, but that temperature dependence is often negligible, it's often small, and often neglected. Now let's look at these two equations again. The Arrhenius equation, K is A times e to the power of negative activation energy over RT. Irene equation, K is kBT over H times e to the power of negative, well, Gibbs energy of activation over RT. From the Arrhenius equation, we know Ln(k) is Ln(a) minus activation energy over RT. If we assume the activation energy is independent of temperature, it's a reasonable assumption, and then we have the first derivative of Ln(k) with respect to temperature is simply Ea, the activation energy over RT squared. Now let's look at the array equation. We take the logarithm of k. Ln(k) is Ln kb over h plus Ln t minus, well, this is the Gibbs energy of activation over RT. And because Gibbs energy and the change in Gibbs energy heavily depends on temperature, we want to make sure to separate G. G should be H minus Ts. Delta G in this case is delta H minus T delta S. So we have this equation over here. This Ln T comes from kBT over H. And over here we have negative enthalpy of activation over RT and plus entropy of activation over R. Now let's assume the enthalpy of activation and the entropy of activation are both independent of temperature. We can take the first derivative of Ln(k) with respect to temperature. We get 1 over T, it comes from Ln T, and then minus 1 over R. And then over here, this is the first derivative of this guy. Alright, delta H over T, and then we have 1 over T plus the enthalpy of activation over RT squared. Now let's look at this from our equation. d Ln k over dt is Ea over RT squared. Let's look at this equation from the Irene equation. d Ln k over dt is 1 over T plus the enthalpy of activation over RT squared. So we have these two equations side by side. They're both how Ln k depends on T, so I'm going to put an equal sign in between. So the activation energy over RT squared is approximately 1 over T plus the enthalpy of activation over RT squared. Therefore, we proved the activation energy is equal to RT plus the enthalpy of activation. We do have approximate sign here because the Arrhenius equation is not exact. So this is a approximate equation for computing rate constant K. And E sub A, well, may slightly depend on temperature. And also, when we take the first derivative over here and over here, we are assuming this enthalpy of activation and entropy of activation are completely independent of temperature. So we did make approximations. We want to emphasize the approximation by using this approximate sign. Again, the activation energy is approximately the enthalpy of activation plus RT. Again, we assumed this enthalpy of activation and entropy of activation are both independent of temperature. Well, this is just because the isobaric heat capacity of the transition state is often very close to the isobaric heat capacity of the reactants. We can write out the temperature dependence of the enthalpy of activation and also for entropy of activation. You can see this enthalpy of activation at T2 is equal to enthalpy of activation at T1 plus this integral of delta CPM dt. And this integral is often smaller than this item or this item. Therefore, we often say, well, the enthalpy of activation is approximately independent of temperature. What about entropy of activation? Well, the entropy of activation at T2 equals the entropy of activation at T1 plus the integral of delta CPM dt over T. And again, this integral is typically smaller than this item or this item. So approximately we say the entropy of activation is approximately independent of temperature as well. Now, what is this delta CPM with a double dagger in the superscript? It's simply the CPM of the transition state minus the CPM of the reactant. Delta CPM is often in the order of 10 to the power 1 joule per mole Kelvin. And if you integrate this over a narrow or moderate temperature range, well, the integral of delta CPM is, I think, roughly in the order of 0.1 kilojoule per mole, while delta H is often tens or even hundreds of kilojoule per mole. That's why this integral is negligible. And over here, if you look at again a small temperature range, and then you look at the value of this integral, it's often in the order of 10 to the power 0 joule per mole per Kelvin, and that's usually much smaller than the entropy of activation, and therefore we often neglect this integral and assume the entropy of activation is also independent of temperature. Previously, we said the activation energy is equal to the enthalpy of activation plus RT. But if we assume both EA and delta H are independent of temperature, why the difference between these two depends on temperature? Again, if you look at this, the activation energy minus the enthalpy of activation is approximately RT. So that's dependent on temperature. But we did assume the activation energy is independent of temperature. We assumed enthalpy of activation is independent of temperature. But now the difference depends on temperature. Why is that? Well, again, it's just because the Arrhenius equation is inexact. E sub A might slightly depend on temperature as well. And also delta H and delta S do depend on temperature. It's just the dependence is small. However, when we derive, d ln k over dt, we completely neglected the temperature dependence of the enthalpy and entropy of activation. Now, even if we have this equation, sometimes we say delta H of activation is roughly the activation energy. Why is that? Because RT is often much smaller than the activation energy and also much smaller than enthalpy of activation. So we can also, approximately say the activation energy equals the enthalpy of activation. It's reasonably accurate at low temperature. For example, RT is only 2.5 kilojoule per mole at room temperature. RT is only 3.3 kilojoule per mole at 400 Kelvin. And the activation energy, the enthalpy of activation of most reactions are typically in the order of tens of kilojoule per mole. So that means, well, this RT is usually much smaller than delta H. This RT is usually much smaller than E sub A, and therefore approximately E sub A is equal to the enthalpy of activation. Again, from the Arrhenius equation, we can take the logarithm of k. ln k is ln kBT plus ln T minus the Gibbs energy of activation over RT. And we do need to separate this delta G into delta H and T delta S in this manner. Note that we have over here T delta S on top and RT on the bottom, so T and T cancel. And now we can actually move this ln T to the left hand side. So ln k over T is a linear function of 1 over T. The slope is negative enthalpy of activation over R. The intercept is ln kB over H plus the entropy of activation over R. If we assume delta H and delta S are independent of temperature, then this graph is linear. We can plot ln k over T versus 1 over T, get the intercept, get the slope, and then we can determine the enthalpy and entropy of activation. Again, the slope is negative enthalpy of activation over R. The intercept is the natural logarithm of kB over H plus the entropy of activation over R. So again, if you just generate a plot of ln k over T versus 1 over T, we can get the slope and intercept simultaneously and then determine the enthalpy and entropy of activation quickly. From the Arrhenius equation, we have Ln(k) equals Ln(a) minus the activation energy over RT. A is the pre-exponential factor. And we usually assume this A is independent of temperature, and then the slope of Ln(k) versus 1 over T is negative activation energy over R. The intercept of Ln(k) versus 1 over T is the natural logarithm of the pre-exponential factor A. So this way we can compute the activation energy and the pre-exponential factor given the plot of Ln(k) versus 1 over T. So now let's compare this two side by side. Given the Arrhenius equation, we need to make a plot of Ln(k) over T versus 1 over T. For the Arrhenius equation, we need to generate a plot of Ln(k) versus 1 over T. The vertical axis is different. We have Ln(k) over T here, and we have Ln(k) directly from the Arrhenius equation. Now let's look at one numerical example from 12.5.1. Let's determine the activation energy and the enthalpy of activation for an elementary reaction from A to P with a reaction rate constant of 0.02 per second at 400 Kelvin and 2 per second at 500 Kelvin. And you can see as the temperature goes up from 400 to 500 Kelvin, the rate constant increases from 0.02 to 2 per second. That's a big increase by a factor of 100. Now let's look at the slope of Ln(k) over T versus 1 over T. The slope is negative delta H over R. This delta H with double dagger is the enthalpy of activation. So we can either make a graph or we can do this calculation by hand. So the slope is simply, remember, delta y over delta x if you're looking at the slope of y versus x. So really it's the change of the vertical axis divided by the change of the horizontal axis. The vertical axis is Ln(k) over T. The horizontal axis is 1 over T. We do this calculation, we get the slope negative 8,764 Kelvin. We compute the enthalpy of activation to be 72.9 kilojoule per mole. Now we're going to do the analysis assuming the Arrhenius equation can be used for this reaction, and then we plot Ln(k) versus 1 over T. The slope is now negative activation energy over R. Again, the slope is just delta y over delta x, with y as the vertical, x is the horizontal. So delta y is just the difference between the Ln(k) values, and delta x is the difference between 1 over T values. We get negative 9,210 Kelvin. We calculated this activation energy to be negative R multiplied by the slope. It's 76.6 kilojoule per mole. You can see the activation energy and the enthalpy of activation are really close to each other, 72.9, 76.6, but they do differ. If you take the difference between these two, it's actually roughly RT. So if you do activation energy minus the enthalpy of activation over R, you get 446 Kelvin. And let's look at the temperatures. It's 400 Kelvin, it's 500 Kelvin. So the difference between activation energy and the enthalpy of that activation is roughly, well, a temperature between 400 Kelvin and 500 Kelvin. Again, we verify this equation numerically. The activation energy is approximately equal to RT plus the enthalpy of activation. Chapter 12, Elementary Chemical Kinetics, Section 12.6, Potential Energy Surfaces. A potential energy surface describes the potential energy of a molecule as a function of the relative positions of the atoms. One example is the potential energy of butane versus the carbon-carbon dihedral angle of butane. So we can look at this molecule from this direction, and you can see we can rotate the single bond between carbon 2 and carbon 3 to have different dihedral angles ranging from 0 to 360. And between 0 and 360, we have different conformations. So over here, we have this 4 carbon atoms on the same plane. It's called same periplanar. And over here, we have a 60 degrees dihedral angle for this carbon 1, carbon 2, carbon 3, carbon 4. Alright, this dihedral angle. And here we have the so-called eclipsed conformation. We have this HCH3 and this H with the same angle. And due to the repulsion, we have higher energy here. And then now here we have this so-called anti-periplanar conformation. The two CH3 groups are opposite to each other. And now we have another eclipsed conformation with higher energy, lower energy, alright, and this is called gauche conformation. Finally, we get back to the 0 degrees or 360 degrees. So you can see there's a repulsion between these two methyl groups. There's a repulsion, smaller repulsion between these two hydrogen atoms and between these two hydrogen atoms. This is called same periplanar versus this anti-periplanar. And also we have gauche conformation with lower energy and eclipsed conformation with higher energy. So this is the potential energy surface of butane with the dihedral angle of carbon 1, 2, 1, 2, 3, 4 as the horizontal axis. Here's another example of potential energy surfaces. Let's look at a reaction from A plus BC to AB plus C. So in the reactant structure, we have a BC bond. A is far away from B and C. And on the product side, we have the AB bond, and then C is far away from AB. So now let's look at a graph over here. This is a two-dimensional contour plot of the potential energy surface. So I want to look at this green dot over here. This is actually the transition state. The transition state for this chemical reaction. In this transition state, we have partially formed AB bond and partially broken BC bond. So this is over here, and right here, you can see we have a smaller BC bond distance, right? So this is the bond distance of BC. We have a smaller BC bond distance. Over here we have a larger BC distance. So right here at this point we have a BC bond. We have a BC bond with a short distance between B and C. And A is far away, so AB is pretty high. Okay, our AB is pretty large. And then you can go through this minimum energy path or intrinsic reaction coordinates. We go to this side. At this point, AB is short. Okay, AB is short. There's a AB bond. And then how about BC? BC is large. So the BC bond is completely broken here. We have AB bond. So this reaction can be described by this green curve that passes through the transition state, denoted by this green dot. A more specific example of A plus BC to AB plus C is the SN2 reaction between chloride and bromomethane in water. So on the left hand side we have chloride, and in this molecule we have a carbon bromine bond. On the product side we have a carbon chlorine bond, and we have a separate bromide in water. It's a typical SN2 reaction. We can also create the potential energy surface this way, with the potential energy versus the so-called intrinsic reaction coordinate. And this intrinsic reaction coordinate includes the changes in the carbon-bromine bond distance and carbon-chlorine bond distance. In addition, this intrinsic reaction coordinates include the changes of the coordinates of these 3 hydrogen atoms relative to carbon. So you can see this is almost planar. This CH3 is almost planar. Over here it's definitely non-planar. On the product side it's non-planar. In the middle it's planar. So the intrinsic reaction coordinates just describe the changes of the coordinates of the entire molecule. And now you can see on the left hand side we have chloride and bromomethane. On the right side we have bromide and chloromethane. In the middle we have the transition state structure. So using a computational chemistry program, we can compute first the transition state and then do a intrinsic reaction coordinate calculation. We'll get some other structures along this minimum energy path to the left and also the minimum energy path to the right. And now we know more about this entire reaction path, not just the reactant, not just the product, not just the transition state, but some intermediate structures in between. Chapter 12, Elementary Chemical Kinetics. Section 12.7, Reversible Reactions and Chemical Equilibrium. Reversible reactions are not elementary because they involve 2 steps, forward and reverse. When both the forward and reverse reaction steps are elementary, we can write out this mechanism with 2 reaction steps from A to B and from B to A separately. From A to B, we have a rate constant denoted by K sub A. From B to A, we have another reaction rate constant denoted by K sub B. Now let's look at dA over dt. It's equal to KBB minus KA because A is consumed in the forward step. A is produced in the backward or reverse step. Therefore, we have 2 terms here, and from A to B, the reaction rate is KAA, and that's why you have that here. There's a negative sign in front because in this step, A is consumed. In the second step, A is produced. Therefore, we have positive KBP, KB times B, where KB times the concentration of B is the reaction rate for this reverse step. What about dB over dt? Well, B is consumed in the second step with KBB as the reaction rate, and B is produced in the first step with a rate of KAA. Therefore, dB over dt is KAA minus KBB. If you add up these 2 equations, you're going to see dA over dt plus dB over dt is equal to 0. These 2 cancel, these 2 cancel. That means A plus B remains constant. Why is that? Well, it's just because when A is consumed, you produce the same amount of B. If B is consumed, you generate the same amount of A. So the sum of A and B never changes. Now, for simplicity, let's assume the reaction system does not contain B initially. That means at time 0, B naught is 0. And therefore, A plus B is always equal to just A naught. B is just A naught minus A. Well, what if there's B at the beginning? Well, then B is A naught plus B naught minus A. Alright, but that's just slightly less convenient. Now let's assume B naught is 0. Then we have this equation. dA over dt is KBB minus KA. And the concentration of B is A naught minus A. So we plug that in. And then we need to solve this equation. How? Well, first separate the variables. We have dA over this entire equation of A equals dt. Then we integrate both sides. The derivation is non-trivial, but if you are good at integral calculus, you will get to this. A is A naught times a fraction. On the bottom we have Ka plus Kb. On the top we have Kb plus the product of Ka and exponential function. The exponential function is e to the power of negative k plus kb multiplied by time. So we have that equation for a here. A is just a naught times a fraction with k plus kb on the bottom, with kb plus a product of ka and an exponential function on top. E to the power of negative ka plus kb times multiplied by time. What about b? B is a naught minus a. So we just use a naught minus this expression, and we'll get just ka minus ka times the same exponential function on top, k plus kb on the bottom, and then multiply by a naught. We can verify these two equations at time 0 and time infinity. Time 0 is very simple. You just plug in t equals 0 here, and on top you have kb plus ka, on the bottom you have ka plus kb. Therefore a is just a naught. What about b? Well, b is a naught minus a. Alright, when a is a naught at time 0, then b is just 0. So we can verify these two equations at time 0 easily. At time equals infinity, well, same thing. We just plug in time equals infinity here, and this exponential function becomes 0, and this one also becomes 0. And therefore, we have also two expressions for a and b. A is kb over k plus kb times a naught. B is ka times divided by ka plus kb, and then times a naught. Now look at this. If you sum them up, of course you get a naught, because on top you'll get kb plus ka. On the bottom you have ka plus kb. So a plus b is equal to a naught. That's good. Now let's look at b over a. When time is equal to infinity, what is b over a? Well, that's just the equilibrium constant, right? The concentration of the product divided by the concentration of the reactant at equilibrium. We're assuming when the time approaches infinity, the reaction approaches its chemical equilibrium. Alright, so we have b over a is the equilibrium constant for this reaction. And also, if you use these two equations, b over a is ka over kb. A naught cancel, k plus kb cancel, and again, b over a is just ka over kb. And that also makes sense, because when you look at this equation, that tells you ka times a equals kb times b. Ka times a is the forward reaction rate. kb times b is the reverse reaction rate. And we know at equilibrium, well, the forward and reverse reaction rates are the same at equilibrium. So everything makes sense here. Again, the equilibrium constant is the forward reaction rate constant over the reverse reaction rate constant. You might have learned this in general chemistry. Now let's look at one numerical example problem, 12.7.1. In a reversible reaction mechanism, we have two elementary steps, from A to B and from B to A. Let's say the initial concentrations of A and B are 0.3 molar and 0.1 molar. So we're making it more general. We allow B to exist at the beginning, and the Ka and Kb are 0.009 per second and 0.001 per second. Now let's calculate the concentrations of A and B. When the reaction reaches equilibrium, at equilibrium we have the forward reaction rate equal the reverse reaction rate. So Ka is equal to Kbb. And then we have 0.009 times A equals 0.01 times B. Therefore, B should be 9 times the concentration of A at equilibrium. Again, I have this equation because at equilibrium, the forward and reverse reaction rates are equal. And then we get this conclusion, B is equal to 9 times A. At equilibrium, we have B plus A is equal to 0.1 plus 0.3. So that's 0.4. Why is that? The sum of B and A never changes. So we have this 0.4. Now we have two simple equations. B is equal to 9 times A at equilibrium. B plus A is 0.4 at equilibrium. So how do we solve this? Very simple. two linear equations, two variables. Just solve them, you get the final concentrations of A and B at equilibrium. For A, it's 0.04. For B, it's 0.36. We can easily verify these two numbers. This B concentration is 9 times A, and the sum is 0.4. Chapter 13, Complex Reaction Mechanisms. Section 13.1, Parallel and Sequential Reaction Mechanisms. In a parallel reaction mechanism, 2 plus reactions proceed in parallel. For example, we can have two elementary steps, from A to B and from A to C. From A to B, we have a rate constant, denoted by K sub B. From A to C, we have a different rate constant, denoted by K sub C. So over here, we have a picture that serves as an analogy. So we have a lot of water in A, and then, well, just imagine the water may flow down this pipe B or this pipe C. So overall, the flow rate will be the flow rate in pipe B plus the flow rate in pipe C. So A is consumed via both elementary reaction steps in parallel. So the flowing is going on in both pipe B and pipe C. Therefore, dA over dt, that's the change of the concentration of A over time, is equal to negative kBA minus kCA. But over here, kBA is the reaction rate for this A to B. kCA is the reaction rate of A to C. So together, we have the consumption rate of A. We can combine kB and kC, and therefore dA over dt is equal to negative the sum of kB and kC times A. The production rates of B and C are different. dB over dt is just kBA. That's the reaction rate of the first step. dC over dt is kCA, the reaction rate of the second step. Well, if we look at these three equations, they are all differential equations, but only the first one can be solved directly. The reason is, in the first differential equation, you have only two variables, the concentration of A and time. That's it. But over here, in this differential equation, there are three variables. You have B, A, and T. Here we also have three variables, A, C, and T. We cannot solve the bottom two differential equations. However, we can solve this one because there are only two variables, and we can separate the two variables easily. So both sides divided by the concentration of A, and both sides multiplied by dt. We have this equation. Now we can integrate both sides. And then we have the natural logarithm of A is equal to negative the sum of kb and kc multiplied by time, and then plus a constant. We can determine this constant. If the initial condition is this, A equals A naught when time equals 0, we plug in the initial condition here and here. We'll see this constant is equal to the natural logarithm of A naught. And therefore, ln A is negative kb plus kc times t plus ln A naught. And therefore, A is A naught times e to the power of negative kb plus kc multiplied by time. And you can see this A decreases exponentially, and sometimes we call this exponential decay. And it just resembles the simple first order reaction rate. Again, the concentration of A decreases exponentially in this parallel mechanism. A is A naught times e to the power of negative kb plus kc times t. And sometimes you can just define K effective to be kb plus kc. And it looks like just the first order elementary reaction with a effective rate constant being the sum of kb and kc. Now, given this differential equation, this differential equation, and this differential equation for the three species, we can sum up the three equations. Therefore, the first derivative of a plus b plus c with respect to time is equal to 0 in the end. So you can see all this cancel. KBA and KBA cancel, KCA and KCA cancel. That means a plus b plus c never changes with time. So if we look at this graph, assuming initially there's only A, and then this water can flow into B and C, but overall the amount of water never changes. That's just another analogy for this. A plus B plus C never changes. So if 1A is consumed, it becomes either 1B or 1C, but the sum never changes. Assuming B naught is 0, C naught is 0, and then B plus C is A naught minus A, which is simply A naught times 1 minus this exponential function. And also, if B naught is 0 and C naught is 0, we know B over C is going to be, well, B naught plus the change of B over C naught plus the change of C. And if B naught is 0, C naught is 0, we have this. B over C is the change of B over the change of C. So again, the change of B over the change of C is equal to B over C. So we just need to get a ratio between B and C. And this delta B over delta C is dB over dC. Okay, because we can just integrate both sides, or we can have this delta approach 0 or approach infinitesimal, and we get this. We know dB is kBA dt from this equation. Alright, dB is kBA times dt, and dC is kCA times dt. dt and dt cancel, A and A cancel, so we have kB over kC. So really, the change of B versus the change of C is kB over kC. That does make sense, because kB and kC are the indicators of how fast A is converted to B versus A converted to C. And now we can solve two equations for B and C. One equation is this: B over C is kB over kC. The other equation is this: B plus C is A naught times 1 minus this exponential function of negative k effective t, where k effective is kb plus kc. So assuming B and C are two variables and we have two equations, we'll just solve those two equations. We get B and C. They look very complicated. B is kb over this k effective times A naught times 1 minus the exponential function. C is kc over this k effective times A naught times 1 minus the exponential function. Again, I was just using k effective as the sum of kb plus kc. And we can also verify that B over C is simply kb over kc. You can just compare the right hand sides of these two equations. They differ only here and here. Kb over kc is equal to B over C. And also, you can verify by these two equations by adding up B and C. B plus C is this plus this times A naught times 1 minus the exponential function. And you can see this fraction plus this fraction is exactly 1. Now let's look at one numerical example problem, 13.1.1. In this following parallel reaction mechanism, A is converted to B, A is converted to C, A is converted to D, all simultaneously. And we have the values of KB, KC, and KD, 2 per second, 3 per second, 5 per second. Now we can calculate the concentrations of A, B, C, and D at time equals 0.2 seconds, given the initial concentration of A, which is 0.2 molar. We can also compute the concentrations of A, B, C, D when time approaches infinity. And of course, when time approaches infinity, obviously A should be 0. All of A is consumed. But now let's look at this condition. At time 0.2 second, we'll just plug in this equation. A as A naught times e to the power of negative K effective t. So K effective is the sum of KB, KC, and KD. Alright, and then the sum is negative 10. The sum is 10 per second. So we plug in all the numbers, the initial concentration, negative K effective, and multiply by time. So you can see we have 0.2 molar times e to the power of negative 2. The result is 0.027 molar. So at time 0.2 seconds, the concentration of A drops to 0.027 molar. And therefore, B plus C plus D is equal to 0.2 minus 0.027. Why is that? Well, the sum of the concentrations of all these four species should be a constant. And in this case, the sum should be 0.2 molar. So we're using 0.2 molar minus the concentration of A. We get the sum of BCD, 0.173. And now the ratio between B and C and D is always 2 over 3 over 5. Again, we have a ratio among the three rate constants, 2, 3, and 5. And therefore, BCD should be 2, 3, and 5. Alright, so now let's distribute this 0.173 molar to B and C and D proportionally. So for B it's just 2 out of 10, for C it's 3 out of 10, for D it's 5 out of 10. And then we get all these numbers for B, C, and D. When time approaches infinity, of course A is completely consumed, A is 0, then B plus C plus D is 0.2. So all of A has been converted to either B or C or D. But how much? Again, let's look at the ratio. B over C over D is equal to 2 over 3 over 5. And then we can simply solve the equations. We get the concentrations of B as 2 over 2 plus 3 plus 5 multiplied by this total concentration. We get 0.04 molar. Similarly, we get the concentrations of C and D. We learned the parallel mechanism and worked on one numerical example. Now let's work on this sequential reaction mechanism. In a sequential reaction mechanism, 2 plus reactions proceed in sequence. So over here, this diagram shows that for A, for the water in A, to reach P, it has to pass through this pipe I. Alright, so this is done in order, from A to I first and then from I to P. You cannot go from A to P directly. You have to pass I first. And this is the simplest sequential mechanism, and we can write out the mechanism this way, from A to I and then from I to P. We need some notations for the rate constant, so from A to I, we use k sub A as the rate constant. From I to P, we use k sub I to denote the rate constant. I is considered the intermediate from A to P. Since we have 3 chemical species in the mechanism, we should be able to write out 3 differential equations. Why is that? The concentrations of A and I and P all change with time. So we can have an equation for dA over dt, another equation for di over dt, and a third equation for dP over dt. Now let's look at dA over dt. A is involved in only the first step, from A to I, and it's consumed. Therefore, we have a negative sign here. And how fast is this? Well, the rate is Ka times A. Now let's look at dP. dP over dt is Ki times I, only because P appears in only the second step, from I to P. P is produced, therefore you have a positive expression over here. And how fast is this? Well, it's just K sub I multiplied by I. So we have these 2 equations. Finally, let's look at di over dt in this sequential mechanism. I is produced in the first step, a positive expression. I is consumed in the second step, therefore a negative expression. And you can see the rate of the production of I in the first step is Ka times A. And the consumption rate of I is Ki times I. So you have the 3 differential equations. We might assume only A exists at time 0, so I naught is 0, P naught is 0, and therefore A plus I plus P is equal to A naught at all times. Now we're going to solve the first differential equation. It's easy because we have only 2 variables, and this is just the simple first order elementary reaction. We solve it, we get a equals a naught times e to the power of negative kat, and therefore di over dt is ka times a minus ai times I, and now we can replace a with a naught times e to the power of negative kat. If you look at this equation, we have also only two variables, I and t. Alright, but it's not trivial to solve this differential equation. We have some strategies to solve this kind of differential equation. One strategy is to make an educated guess of the expression of I. So I'm making a guess here. I see this exponential function here, so I'm assuming I is a constant times that exponential function. And also, if I delete this part, if I have just di over dt equals negative kii, well, this concentration must contain an exponential function like e to the power of negative kit. So I'm just guessing that I is a linear combination of two different exponential functions, e to the power of negative kat and e to the power of negative kit. Now we plug this into here and here. On the left hand side, we just take the derivative of I this way. On the right hand side, we just express this I in terms of linear combination of these two exponential functions. We can try to simplify this equation because I can see there's a kib times e to the power of negative kit. We have kib e to the power of negative kit. So this to cancel. Now we have only 1, 2, 3 terms, and it contains a, so somehow we can just express a in terms of a naught times ka over ki minus ka. Alright, you can see this exponential function and this exponential function and this exponential function disappears because we can just divide both sides by that exponential function. At least we get the expression of a in here. We're going to try to get the expression of b as well. Again, we took an educated guess. We say I is a linear combination of two exponential functions, e to the power of negative kat and e to the power of negative kit. At time 0, we know the concentration of I is 0. Therefore, we plug in I equals 0 here and time equals 0. And then we get a plus b equals 0. That means b has to be negative a, and b is negative ka over ki minus ka times a naught. And now we finally have the analytical expression of I. We know the expression of a, and we know b is negative a, and then we have this expression for I. I is ka over ki minus ka, and then times the difference between these two exponential functions and then multiply by a naught. We can easily verify that this I is 0 when time is 0, this I is 0 when time is infinity. Let's plug in time equals 0. And then you have e to the power of 0 minus e to the power of 0. That's just 0, and then I is 0. What if time is infinity? Well, you have e to the power of negative infinity minus e to the power of negative infinity. That's still 0. So I is still 0. That's all good. We verified that the expression holds when time equals 0, when time equals infinity. The physical meaning is simple, because at the beginning you have only reactant A in the system, so I is 0. And when time approaches infinity, there's only product in the system, so still I is 0. So again, at the beginning of the reaction, I and P are both 0. At the end of the reaction, well, A and I are both 0. There's only P. And in the middle of the reaction, of course, you have a positive concentration of I. That tells us, well, maybe the concentration of I, well, is 0 at first. In the middle, it goes up. And near the end, it decreases until it levels off. Again, we have gotten the analytical expression of I, the intermediate. It looks fairly complex. I is just Ka over Ki minus Ka times the difference between these two exponential functions times a naught. We now do more analysis. especially for two different scenarios. One scenario is what if Ka is much greater than Ki? So Ka is much greater than Ki. You get a negative denominator here, but this is also also negative. So overall, I is still positive. All right. So I has to be either 0 or positive. The concentration cannot be negative. All right. So now let's assume Ka is much greater than Ki. It's one of the several scenarios over here. So what if Ka is much greater than Ki? And then we're gonna just neglect this Ki on the bottom, and we're gonna neglect this e to the power negative Kat over here. All right. Again, Ka is really large. E to the power of negative large number approaches 0. So we got this equation, and of course K and K can cancel. Negative sign and negative sign can cancel. So I is equal to A naught times e to the power of negative Ki multiplied by time. Well, what does that mean? Well, this means in this scenario, when Ka is much greater than Ki, well, A is converted to I really quickly. So this reaction mechanism may be treated just as a simple I to P elementary reaction, because again, just as long as the reaction starts, all A is gone. There's no A in the system, so it's only I to P. It's only I to P, and the initial concentration of I is just A naught. All right, so that's why we have a simple expression over here. This is just the first order decay of I. What if Ka is less than Ki? This is actually more common because later we'll see usually I is fairly energetic, and then K is usually small, Ki is usually big. When that's the case, again, we're going to make approximations. Since Ka is much smaller, we can neglect this. And since Ka is smaller, Ki is larger, this exponential function approaches 0. Now we have the expression of I again. It's equal to Ka over Ki times A. And then in this case, we see, since I is equal to Ka over Ki times A, we can rearrange this equation. We get Ka times A equals Ki times I. What does this mean? Well, Ka times A is the production rate of I. Ki times I is the consumption rate of I. And when this approximation holds, well, somehow di over dt is close to 0, because di over dt is Ka minus Ki, and we're saying this two are about the same if Ka is much smaller than Ki. And we have a approximation here. Di over dt is roughly 0 if Ka is much smaller than Ki. And this is the so-called steady state approximation for I. Well, that's di over dt is approximately 0. That means the change of I, well, is very close to 0. Why is that? Well, if Ka is much smaller than Ki, that means whenever I is produced, it's going to be consumed almost immediately, really quickly. So the concentration of I is always very low during the reaction. The concentration of I is very low in the reaction, then di over dt cannot be large. So I itself is extremely low during the entire reaction, then di over dt has to be pretty small. And now we have this so-called steady state approximation. Di over dt is approximately 0. And this approximation can be made for unstable, energetic, intermediate species. What if AI and Ka and Ki are exactly the same? And then we're going to use just K to denote both rate constants. This is extremely rare because usually different elementary reactions have just different reaction rate constant. But what if this indeed happens? Well, then we have to solve the differential equation slightly differently. It's going to be this, and then the solution is this. I is Kt times A naught times e to the power of negative Kt. We can still verify this equation is correct when time is 0, when time is infinity. When time is 0, you plug in t equals 0 here, I is 0, and that makes sense. When time is infinity, well, this time approaches infinity, But this e to the power of negative kt approaches infinitesimal faster than this t approaching infinity. So this I is still 0. And that again makes sense. When time approaches infinity, there's only p, the product, in the system. There's no a, there's no I in the system. Again, in the sequential reaction mechanism from a to I to p, a is a naught times e to the power of negative kat. This is exponential decay. And if ka is different from ki, we can derive the expression of I. And over here, I is a function of time. It is proportional to a naught, and then, well, it's proportional to something more complicated. It's proportional to ki and inversely proportional to ki minus ka. That's proportional to the difference between these two exponential functions. And a plus I plus p is always a naught, so no matter how this water in A flows into I or into p, the total amount of water should be constant. So p is just a naught minus a minus I, and we have the expression of a, we have the expression of I, we put them together. This is a fairly tedious expression of the product. But still, we can verify at time 0, p is 0, at time infinity, p is a naught. Let's plug in t equals 0 here, t equals 0 here, and then you have ka over k minus ki over ki minus ka. It's going to be negative 1 here, plus 1, that's 0. So p is 0. What if t approaches infinity? Well, it's just this is 0, this is 0, and overall this is 0. 0 plus 1 is 1. 1 times a naught is a naught. So p equals a naught when time approaches infinity. Now, this is extremely rare. What if ka equals ki? Well, we're going to just use k to denote both ka and ki. We have this equation, and we can rewrite this equation to here because a is a naught times e to the power of negative kt. And we can solve this equation. A is kt a naught e to the power of negative kt, and p is simply a naught minus a minus I. Alright, so this expression is simply a naught minus a and minus I. Again, we can verify this p is 0. When time is 0, just plug in time equals 0 here and here. You get 1 minus 1 minus 0. That's just 0. When time approaches infinity, these two terms become infinity. So p is equal to a naught, and that also makes sense. As time approaches infinity, we have only p in the system. There's no a, no I, it's just p. And p equals a naught. In a sequential reaction mechanism from A to I to P, we have the expression of I. As we verified before, at the beginning, when t is 0, I is 0. When t is infinity, at the end, I is also 0. That means I is likely increasing and then decreasing as the reaction proceeds. And I very likely will have to reach a maximum during the reaction. So how do we theoretically derive when this concentration of I reaches maximum? Well, at the maximum, we know the slope is 0, so we set di over dt to be 0. So the derivative of this expression of I with respect to time should be 0. And now we're going to clean up this equation. A naught does not depend on time, Ka does not depend on time, Ki minus Ka does not depend on time, so we can simplify this way. And then we can take the derivative of these two terms. We get Ka times e to the power of negative Kat equals Ki times e to the power of negative Kit. We take the logarithm of both sides and rearrange. We have the expression of the time when I reaches maximum. It's the difference between the logarithms of Ka and Ki, and also divided by the difference between Ka and Ki. So at time like this, both I and Ki reach the maximum. And Ki is just dp over dt. That means the production rate of P reaches the maximum when time equals this, ln K minus ln Ki over K minus Ki. This is when I reaches the maximum. This is when Kii reaches the maximum. Therefore, it's also when dP over dt reaches the maximum. Again, this is rare to have Ka equals Ki. It almost never happens, but if it does, I'm using K to denote Ka and Ki. And we can solve the differential equation to get I is equal to Kt times A naught times e to the power negative Kt. And again, we can find the maximum of this by setting its first derivative with respect to time to 0, and then we solve this equation. We get this equation, and this equation is really easy to solve. When Kt equals 1, this is 0. So both I and Ki reach the maximum when the reaction time is equal to 1 over K. And when I and Ki reach the maximum, of course dP over dt also reaches the maximum. We have the largest reaction rate expressed as the production of P. Now let's look at one numerical example problem, 13.1.2. In this sequential reaction mechanism from A to I, from I to P, we have two rate constant. K sub A is 0.01, extremely slow. Ki is 300 per second, extremely fast. Let's have the initial concentration of A, which is 0.2 molar. We'll calculate A and P when time is 200 seconds. And we're going to estimate I at also 200 seconds. We'll calculate AI and P when time approaches infinity. So first, at time 200 seconds, A is A naught times e to the power of KAT. We're just plugging all the values. We get 0.164 molar. That's the concentration of A at 200 seconds. I is much smaller than A and P because I, well, if you look at this, the production rate of I is extremely slow. The consumption rate of I is extremely fast. These two numbers differ by 300,000. So once I is produced, it's immediately consumed. And now we're going to use the steady state approximation. That means di over dt is just 0. And that means the consumption rate of I equals the production rate of I. The production rate of I is Kaa, the consumption rate is Kii, so we have this equation. Now we can compute the concentration of this I approximately. It's just Ka times A over I. We have Ka over here. We have A over here at 200 seconds. And then we have K sub I over here. Now we get the concentration of the intermediate I at 200 seconds. It's 0.000000546. We have 7 zeros here, so we know the concentration of I is always extremely low. Why it's low? Because the first reaction is slow, the second reaction is fast. So it takes a long time to produce I, and then once I is produced, it's immediately consumed. Therefore, we cannot have a lot of I. The accumulation of I is extremely hard in the system. That's why it's extremely low, and also because of that, we can say di over dt is also approximately 0. Now let's verify or calculate the concentrations of AIP when the time approaches infinity. When the time approaches infinity, of course, A and I are just 0. There's only P in the system, and P is therefore 0.2 molar. Chapter 13, Complex Reaction Mechanisms. Section 13.2, Steady State Approximation. The simplest sequential reaction mechanism involves two elementary steps. Step 1, from A to I. Step 2, from I to P. I denotes intermediate. There are two different rate constants here. From A to I, it's K sub A. From I to P, the rate constant is denoted by K sub I. Since we have three species involved in the mechanism, we can write out three differential equations. dA over dt is negative Kaa, di over dt is Kaa minus Kii, dP over dt is Kii. If I has a much higher energy than both A and P, it can be very unstable. Both thermodynamically and kinetically. The production rate constant of I is then much smaller than that of its consumption. That means Ka is much smaller than Ki. It takes a very long time to form I from A, but then once I is formed, it's converted to P immediately. And in this case, we may assume that I is extremely low throughout the reaction. The change of the concentration of I with time is therefore negligible. Therefore, di over dt is approximately 0. And we know the analytical expression of di over dt. That's Ka minus Ki. Over here, Ka is the production rate of I, Ki is the consumption rate of I. So we have this approximately equals 0. Using this equation, the concentration of I is approximately Ka times the concentration of A over Ki. And because A is always A naught times e to the power of negative Kat, during the reaction mechanism, we have I is approximately Ka over Ki times A naught times e to the power of negative Kat. For the sequential reaction mechanism from A to I and then from I to P, we can make the steady state approximation for the intermediate I if it's high energy. And then we have I equals Ka over Ki times A naught times e to the power of negative Kat. dP over dt is Ki. This is the exact analytical expression, and we plug in this expression here. Well, dP over dt is approximately Ka, and A is A naught times e to the power of negative Kat. Now we have another differential equation to solve. If the initial concentration of P is 0, we do know P is just A naught minus A minus I, and because I is much smaller than both A and P throughout the reaction, we have this equation, and P is approximately A naught times 1 minus e to the power of negative Kat. We can verify this. We can take dP over dt, and what we will get is going to be A naught multiplied by Ka multiplied by this exponential function, right? So if you take the first derivative of this with respect to time, you get Ka times this exponential function, and then multiply by A0, A naught, it's just this. Now what if the initial concentration of P is non-zero? Well, then P is simply P naught plus A naught times 1 minus this exponential function. When Ka is much smaller than Ki, the production rate of P, dP over dt, equals Ki exactly, is roughly equal to the consumption rate of A, and that's Ka. Well, this is just because once A is converted to I at a very slow rate, I is immediately converted to P. So the rate limiting step of this sequential mechanism is from A to I. Again, Ka is much smaller than Ki, so this reaction is much smaller than this reaction, and this is a sequential mechanism. In a sequential mechanism, the slowest one is the rate limiting step. So the first step is the rate limiting step. And also we know the concentration of I is very low throughout the reaction because it's immediately consumed once produced. In this case, we may assume the steady state approximation for the intermediate I, which is di over dt is approximately 0. Now let's look at a more complex sequential mechanism. Now we have two intermediates. The reaction proceeds from A to I1, the first intermediate, from I1 to I2, the second intermediate, and then from I2 to P. If I1 and I2 are both high energy species, we can make steady state approximations for both I1 and I2. Therefore, di1 is over dt is 0, di2 over dt is 0. The exact expression of di1 is Ka minus K1 I1. The exact expression of di2 over dt is ki k1 I1 minus k2 I2. And it's also roughly 0. And why is that? Well, it's just because I1 is produced in the step from A to I1. The rate is KAA over here. I1 is consumed in the second step. The rate is K1 I1 right here. I2 is produced in the second step. The rate is K1 I1 right here. It's consumed in the last step. The rate is K2 I2, so minus K2 I2 over here. Now if we can use the steady state approximations for both I1 and I2, then we have Ka equals K1 I1 equals K2 I2. So we have these equations. And because dA over dt is negative Ka over A, we have A equals A naught times e to the power of negative Kat. So because A is involved only in the first step, it's just simple first order reaction rate law over here. And dP over dt is equal to K2 times I2 in the last step. And this is equal to K1 I1. And this is equal to KAA. And then we have Ka times A naught times e to the power of negative Kat. If the initial concentration of P is 0, then P is just A naught minus A naught minus A. And this is just A naught minus A. Alright, because the expression of A is A naught times the exponential function, therefore P is A naught times 1 minus that exponential function. What if the initial concentration of P is non-zero? Then we need to include that P naught here in the expression. That's it. The rate limiting step of this sequential mechanism is this, from A to I1, because the production rate P is limited by this slowest step of the sequential mechanism. So again, this Ka is much smaller than K1, the Ka is much smaller than K2. Let's look at one numerical example problem. 13.2.1. We have a complex sequential mechanism for species from A to I1 to I2 to P. We have the values of the three rate constants. Ka, K1, and K2 are 0.001 per second, 300 per second, 500 per second. Well, you can see this case of A is much smaller than K1. It's also much smaller than K2. So obviously from A to I1 is the rate limiting step. Given the initial concentration of A, we can calculate the concentration of A and P at any other time, for example 200 seconds. We can also estimate the concentrations of I1 and I2. Now let's use this first order reaction rate law. At t equals 200 seconds, A is A naught times this exponential function. This is actually exact. This is just first order integrated rate law. We plug in all the numbers, we get 0.164 molar. I1 and I2 are much smaller than A and P, because I1 and I2 are highly energetic. Once they are produced, they are immediately consumed. Therefore, we can assume P is just 0.2, the total, minus the concentration of A, 0.164 at 200 seconds. We get 0.036 molar. Now if we make the steady state approximation for I1, we have Ka equals Ki, K1, I1. We plug in all the numbers. Ka, this is Ka, this is K1. This is the concentration of A at 200 seconds. Now we get the concentration of I1, which is 0.000000546 molar, which is indeed much lower than A and P. We can make the steady state approximation for I2 as well, and then we have K2 I2 equals K1 I1. This is a typo. This is supposed to be I2, and then we compute I2. It's also very small. It's about 3 times 10 to the power negative 7 molar. The rate limiting step, again, it's A to I1, only because this Ka is much smaller than K1. Ka is much smaller than K2. Alright, so it takes a long time for A to be converted to I1, but once I1 is produced, it's converted to I2 immediately. Once I2 is produced, it's converted to P immediately. And this is why both I1 and I2 are really low in the reaction. Chapter 13, Complex Reaction Mechanisms. Section 13.3, Pre-equilibrium Approximation. Consider the following reaction mechanism that consists of three elementary reactions: from A to I, from I back to A, from I to P. The rate constant from I to P is denoted by K sub P. The forward and reverse reaction rate constants in the AI reversible reactions are denoted by K sub F and K sub R, forward, reverse. So the rate constant from A to I is K sub F, from I to A is K sub R, from I to P is K sub P. The pre-equilibrium approximation can be made when K sub F and K sub R are both much greater than K sub P. In this case, we may assume the reactant A and the intermediate I are always at equilibrium. That means Kf times A is approximately equal to Kr times I. So the forward reaction rate from A to I is approximately equal to the reaction rate from I back to A. When we make such approximation, I is roughly A times Kf over Kr. And again, we're assuming K sub P is much smaller than K sub F and K sub R. So in this I to P step, the intermediate I is converted to P so slowly that the decrease of I is very quickly replenished by the AI step, so that the equilibrium between A and I is always maintained, at least approximately. And therefore, we can write out the reaction rate. R is dP over dt, and that's simply K sub P times I. And we have I equals Kf over Kr times A, and then this R, the reaction rate, can be written as K sub P times K sub F over K sub R times the concentration of A. We can define the effective rate constant, K effective, to be Kp times Kf over Kr, and this is the so-called effective rate constant. So you can see it almost like a first order reaction rate. R is proportional to A to the power of 1. We have a rate constant here, but this effective rate constant is equal to Kp times Kf over Kr for this reaction mechanism if we can make this pre-equilibrium approximation. The pre-equilibrium approximation is reasonably accurate if K sub P is much smaller than both K sub F and K sub R. And again, when this I to P reaction breaks the equilibrium between A and I, well, the reactions between A and I respond really quick to restore the equilibrium, at least approximately. Now let's look at one numerical example problem. 13.3.1. Consider the following reaction mechanism that consists of three elementary reactions. Again, we have A to I back to A, and I to P. The forward and reverse reaction rate constants K sub F and K sub R in the AI reversible reactions are 400 per second and 800 per second. K sub P is only 0.002 per second. So you can see this K sub P is much smaller than K sub F and K sub R. That means we can use the pre-equilibrium approximation. Let's assume the initial concentration of A is given. Here, let's say it's 0.6 molar. How do we calculate the production rate of P at t equals 20 seconds using the pre-equilibrium approximation? Alright, now let's do this. At t equals 20 seconds, we can assume the concentration of P is much smaller than I and A, only because the production of P is extremely slow. You can see how slow it is. And then approximately we can say, well, I plus A is equal to A naught, and that's 0.6 molar. Alright, this is an approximation because I plus A is exactly A naught minus P. We're assuming P is really small, it's negligible, therefore I plus A is approximately 0.6 molar. Now let's make pre-equilibrium approximation. Alright, and then I times K sub R is equal to Kf times A. I'm assuming the reaction rate from A to I equals the reaction rate from I to A. And then we have this equation. The concentration of I is approximately Kf over Kr times A. We plug in these values. We have I is roughly 1/2 of A at 20 seconds. And we have the sum, we have the ratio, and then we can compute the concentration of A is 0.4 molar, the concentration of I is 0.2 molar. Now in this step from I to P, the intermediate I is converted to the product P slowly. At 20 seconds, R is dP over dt. The expression is Kp times I. We have the value of Kp. We have the approximate value of the concentration of I. Plugging all numbers, we get a reaction rate. Well, at 20 seconds, the reaction rate is 0.0004 molar per second. And also, by looking at this number, we know at 20 seconds, the concentration of P should be less than this much, because I can only increase, at the beginning. That means this I is probably the largest concentration of I in the first 20 seconds. So this is the maximum production rate of P in the first 20 seconds. That means at most this much P is produced. So at most 0.008 molar of P is produced in 20 seconds. Very likely the concentration of P is less than this, and that means it's much less than the concentration of I over here and A over here. And it's reasonable to just assume the concentration of P is much smaller than I and A. This is just to justify our assumption at the beginning, assuming P is still much smaller than the concentrations of I and A. Just to summarize this pre-equilibrium approximation, it's very important that we make the pre-equilibrium approximation only when the rate constant K sub P is much smaller than K sub F and K sub R. Chapter 13. Complex Reaction Mechanisms. Section 13.4. Lindemann mechanism. For unimolecular reactions in the gas phase, such as from A to P, how can the reactant molecule A accumulate enough energy to overcome the reaction barrier to form P? Lindemann proposed that a reactant molecule A in the gas phase may accumulate enough energy via its collisions with other A molecules. The mechanism is like this. A reaction between A and A produces a star and another A. A star is used to denote the activated reactant A or energized reactant A with enough energy to overcome the barrier to form the product P. This reaction is a second-order elementary reaction. The forward reaction rate is K1 times A times A. Therefore, it's K1A squared. In this elementary reaction, A is consumed and produced at the same time, but at a different rate. So you can see two A's are consumed. And over here 1A is produced. So overall dA over dt is negative 2k1a squared plus k1a squared. Overall it's negative k1a squared. What does this mean? This simply means, well, some of the a's are converted to a star. Therefore, as the reaction proceeds, we'll have fewer a but more a star. A star is produced at this rate, k1 times a squared. So you can see dA over dt plus dA star over dt is 0 if we consider this reaction. A star may collide with another inactivated A, lose energy, and become inactivated itself before it's converted to P. And therefore, we can write out another reaction to describe the inactivation of A star. A star may collide with another A and lose some energy. Now on the product side, we have two reactant A's without enough energy to overcome the barrier. The rate constant is K sub minus 1. So over here again, this is just energy being passed from A star to A. And eventually both reactant A do not have enough energy to overcome the reaction barrier to form the product P. Now in this deactivation of A star, we have dA over dt equals negative. Forward is k minus 1 A star times A. This is the consumption rate of this A. Now we have the production rate of these two A's, therefore we have a coefficient 2 here. 2 times the reaction rate. And overall, A is produced. The rate is A K sub minus 1 A star times A. dA star over dt is negative because A star is simply consumed in this step. It's negative K sub minus 1 A star times A. If we sum up this and this, it's 0. Alright, that means in this reaction, the overall effect is A star becomes A. When both reactions from A to A star and from A star to A are considered, we have these two equations. dA over dt is negative k1 A squared, so it's just the consumption of A plus k minus 1 times A star times A, because over here in this reaction step, overall A is produced. That's why we have a plus sign here. Now dA star dt is k1 A squared. This is positive because A star is produced in this step. A star is consumed in the second step, therefore we have minus k sub minus 1 and then A star times A. So we have these two equations. Again, if you sum up these two equations, you can see A plus A star is constant. These four terms, if you sum them up, it's 0. That means A plus A star is constant. It's true because A may be converted to A star and A star may be converted back to A, but the sum should never change. Now this A star may also be transformed into the product P. And let's look at this third elementary step in this Lindemann mechanism. Assume the rate constant is denoted by K sub 2. The reaction is A star to P. A star has enough energy to overcome the barrier. And then we can rewrite dA star over dt, because we can see in this step A star is produced, in this step A star is consumed. However, there's a third elementary step in which A star is also consumed. So dA star over dt is k1 A squared from this reaction step, minus k sub minus 1 A star A from this step, and then minus k2 A star from the third elementary step. So this is a little complicated because A star is involved in 3 elementary steps. It's produced here, it's consumed here, and here. That's why you have a positive term, 2 negative terms. Now we will apply the steady state approximation to A star. Because A star is energized, its concentration is extremely low throughout the entire reaction. Therefore, we may assume dA star over dt is approximately 0. And again, this is the equation for the steady state approximation for A star. And now we have a differential equation for A star, and also we have dA star over dt is 0, and therefore this differential equation is converted to a much simpler algebraic equation like this. We rewrite this k1 times a squared is k sub negative 1 a star a plus k2 a star. And now we can express A star as a function of A. A star is approximately k1 a squared over k minus 1 a plus k2. So over here. This is the expression of A star during the reaction. If you have the concentration of A, the values of K1, K minus 1, and K2, we will be able to compute A star. The overall reaction rate of the mechanism, which is the production rate of P, is this. The rate is dP over dt. dP over dt is K2 times A star. Well, it's from this equation, from A star to P, the rate constant is K2, therefore the reaction rate is K2 times A star. Now let's look at this equation. We have K2 times A star as the production rate of P, and A star is K1A squared over K minus 1A plus K2. So we have the reaction rate is equal to K2 times this whole expression, which results in K1, K2, A squared on top, K minus 1A plus K2 on the bottom. Now if you really look at the expression of the R, it's not proportional to A. It's not proportional to A squared. Therefore, it's neither a first order reaction nor a second order reaction. This is the based on the mechanism proposed by Lindemann for the unimolecular reactions in the gas phase. Later, we will see this expression can be simplified into first order if A, the concentration of A is extremely high. And this reaction rate can be approximately second order when this A is extremely low. Again, for the A to P unimolecular reaction, the overall reaction rate is the production rate of P. It's dP over dt, written as K2 times A star. And A star is K1 times A squared over K minus 1A plus K2. So we have this expression as the reaction rate for the A to P unimolecular reaction, assuming that the reactant A gets enough energy by doing collisions with other A's. And the K1 is the rate constant to generate A star, the energized A. K minus 1 is the reaction rate constant for the deactivation of A star. Again, this is not a first order or second order, but when the concentration of A is extremely low, we have this K minus 1A is much smaller than K2. We can approximate the bottom to be just K2. Alright, so this is the approximation over here, from here to here. I'm assuming k minus 1 times A is much smaller than K2. Just put K2 on the bottom, and then the reaction rate is approximately K1 times A squared. The reaction rate is proportional to the concentration of A squared. It's second order. Now, if the concentration of A is extremely high, we have this K minus 1 times A is much greater than K2 over here, then this reaction rate is going to be first order. Let's look at the approximation over here. Assuming K minus 1A is much greater than K2, we will neglect this K2, and then we have this expression. A squared over A is just A. Now the reaction rate is proportional to the concentration of A to the power 1. It's first order. And the effective rate constant is K1 times K2 over K sub minus 1. Right? We have this effective rate constant, K sub effective, that can be determined given the values of K1 and K minus 1 and K2. And the reaction rate is simply the effective rate constant times the concentration of A to the power of 1. It's pseudo first order. Only if the concentration of A is very, very high. Now, what if a large amount of helium or other inert gas is added into this unimolecular reaction from A to P? What will happen? Well, in this case, the inert gas does not behave only as spectators. Alright, A may collide with those inert gas particles and gain energy. A star may collide with those inert gas particles and lose energy. Alright, so we just use M to denote medium, such as helium or argon. So A may collide with M to be energized. We get A star plus M. A star may lose energy to the medium and become A deactivated plus M. Again, we're going to use K sub 1 and K sub minus 1 as the forward and reverse rate constants here and here. Again, this M denotes medium. It's not just a spectator. It helps activate A and deactivate A star via collisions. And again, A star may be transformed into the product as well. The reaction is from A star to P. The rate constant is K2. And the rate is minus K2 A star. This is how fast A star is consumed in this elementary step. Again, we can apply the steady state approximation for A star because it's energetic, its concentration is extremely low throughout the entire reaction. Therefore, the change of A star with respect to time is negligible. So dA star over dt is 0. And we can look at the change of A star in this reaction. It's produced here. So we have positive K1 times A times M over here. A star is consumed here, and that's minus K sub minus 1 A star M. A star is consumed here. It's negative K2 A star over here. So overall, this is how the concentration of A star changes with time. It's approximately 0 based on the steady state approximation being made for A star, a energized species. Now, given this equation, A star is K1 times A times M over K minus 1M plus K2. M is the concentration of those spectator gas particles, such as helium atoms. The overall reaction rate is dP over dt. It's K2 times A star, so we have K2 times this expression. That's K1, K2, A and M on top, K minus 1M on the bottom, plus K2. And this mechanism is approximately first order when M is extremely high, or second order when M is extremely low. We can just analyze over here. If M approaches infinity here, K2 is neglected, and then you have M and M cancel. It becomes first order, and the effective rate constant is K1, K2 over K minus 1. Alright, and what if M approaches 0, we neglect this m term on the bottom, and overall this reaction rate is going to be K1 times A times M, because K2 and K2 cancel, so this reaction becomes second order and the rate constant is K1 when M is extremely low. That's just the mathematical analysis. Alright, again, when a large amount of helium is added to this unimolecular reaction system from A to P, the inert gas particles are not just spectators. They collide with A to form A star. They collide with A star to form A. And the overall reaction rate is this. It's K1, K2, AM on top, K minus 1M plus K2 on the bottom. It's not a first order reaction. It's not a second order reaction. Alright, but then how do we analyze this kind of equation when we have experimental data of reaction rate versus M? Well, we can simply take the reciprocal of R. And then this is to separate this two. Okay, if we take the reciprocal of the rate constant R, 1 over R is the reciprocal of this. Now K1M plus K2 are flipped to the top. And then we can separate this two, of course, now. And over here, this part, we have M and M cancel, and we get K minus 1 over K1, K2A. Over here, K2 and K2 cancel. We have 1 over K1 AM, and this two terms together is 1 over R. Now we can plot 1 over R versus 1 over M. You can see 1 over R is the linear equation of 1 over M. The slope is 1 over K1A. The intercept is K minus 1 over K1, K2A. So again, we have the y-intercept right here, and the slope is this. This is the slope. We have both the slope and the intercept. If we can plot the reciprocal of R versus the reciprocal of M. And also the slope divided by the y-intercept is K2 over K minus 1. So you can see this divided by this, we'll get K2 over K minus 1. Now what if M approaches infinity? Well, when M approaches infinity, over here 1 over M is just 0, and we have 1 over R equals this, and that's actually the intercept. And also we can flip both sides. R is K1, K2A over K minus 1. Against first order, we have a effective rate constant, which is K1, K2 over K minus 1. This is the maximum reaction rate. Alright, when M approaches infinity, this expression is the maximum reaction rate over here. What if M approaches 0? When that's the case, when M approaches 0, this 1 over M approaches infinity, and then this finite term can be neglected. So 1 over R is this part, 1 over K1 times A times M, and therefore, so it's here, and then R is K1 times A times M, it's second order. It's first order with respect to A, but also first order with respect to the concentration of the medium. Overall, it's second order. Why it's second order? Because when M approaches 0, that means it's hard for A to collide with M to be energized. Now the first step of forming A star is the limiting step. The rate limiting step is the collisions between A and M, and therefore overall the reaction rate is the rate of the limiting step, and the limiting step has a rate of K1 AM, and therefore overall the reaction rate is also K1 AM. So if a mechanism has a reaction rate or has a rate limiting step, then the rate of that limiting step is the overall reaction rate. By the way, we can also make a graph of 1 over R versus 1 over the concentration of the medium molecules. It's linear. The slope is 1 over K1A. It's right here in front of 1 over m, and there's intercept. The intercept is k minus 1 over k1 k2a, so over here. So it's possible for us to collect some experimental data of the reaction rates at different concentration of the medium molecules. But when you make the graph, you have to take the reciprocals of R and M, and then it's called a double reciprocal plot. Again, when very high concentration helium or other inert gas is introduced into the unimolecular reaction system from A to P, the inert gas particles collide with A very frequently, and we can assume there's a ultra fast equilibrium between A and A star. All right, it's just if M is infinity, the forward is fast, the reverse is fast. Remember, when that's the case, we can use the pre-equilibrium approximation. All right, so the rate constant, the reaction rate from A star to P, all right, is much slower than this two. All right, so we're gonna just assume these two reactions are so fast that A and A star are always at equilibrium. So A star and A are always at equilibrium. It's just because in the third elementary reaction from A star to P, once A star is consumed, it's going to be replenished really quickly by this step. And we can assume these two forward and reverse reaction rates are always approximately the same, and that's called pre-equilibrium. So we're going to make this assumption, and then K1AM is equal to K minus 1 A star M. All right, forward is equal to reverse, and then we have A star equals K1 over K minus 1 times A. And then the overall reaction rate is R equals dP over dt equals K2 A star, and A star is K1A over K minus 1. So we have this first order, pseudo first order expression. The reaction rate is proportional to A to the power of 1. The effective rate constant is K1, K2 over K minus 1. So in summary, when M, the concentration M, the medium molecules approach infinity, we can make this pre-equilibrium approximation. We can assume these two reactions are really fast and they are always at equilibrium. So we have this equation, and then we get this first order expression for R. But also remember, previously we used the steady state approximation for A star to get the same expression, all right, for this. As long as M approaches infinity, we have this first order reaction. So anyway, in the end, no matter we use the steady state approximation or pre-equilibrium approximation, if we use these two different approximations for the same scenario, in this scenario, very high concentration helium or other inert gas or other medium molecules, very high concentration. So for the same scenario, and if we make those approximations reasonably, we will end up with the same result. The reaction rate, the overall reaction rate is dP over dt. It's approximately K1, K2, A divided by K minus 1. Again, in this scenario, very high concentration helium, we'll get this. The reaction is going to be pseudo first order. Chapter 13, Complex Reaction Mechanisms, Section 13.5, Adsorption and Desorption. In the adsorption and desorption mechanism, a critical parameter in evaluating surface adsorption is the fractional coverage, theta. Theta is defined to be the number of occupied sites over the total number of adsorption sites. So in this diagram, we can see 1, 2, 3, 4, 5, 6, 7. 7 sites, 7 surface sites are occupied. And now we have some unoccupied sites. I think if you count the unoccupied sites, we have 14 of them. So theta in this case is 7 over 21. The total number of sites is 21. 7 are occupied, so theta is 7 over 21, which is 1/3 in this case. The adsorption, desorption reactions can be expressed as these two equations. So R is the reactant in the gas phase. M denotes the surface sites. They react to form Rm, so occupied the surface sites. Alright, this is Rm. At the same time, this Rm, this absorbed species, may undergo desorption, alright, and to form R and a unoccupied site again. Alright, so these two equations can be used to describe the adsorption desorption mechanism. Okay, R is the species in the gas phase. M is the unoccupied surface sites. Rm is the occupied surface sites. So in this diagram we have 7 Rm, 1, 2, 3, 4, 5, 6, 7. The 7 are considered Rm. And we have 14 Ms. Those are unoccupied sites, 14 blue ones. And we have this R, the blue ones in the gas phase. Again, R parenthesis G stands for the gas phase reactants. M stands for the unoccupied adsorption sites. Rm stands for the adsorption sites that is already occupied by R. Now, the adsorption rate is K sub A, the rate constant, times the pressure of R. So we have a P here, times the number of available surface sites or unoccupied surface sites, which is N times 1 minus theta. Alright, theta is the percentage of the occupied sites. So 1 minus theta is the percentage of the unoccupied sites. And this uppercase N denotes the total number of sites. Alright, again, this is the adsorption rate. Now let's look at the desorption rate. Well, it's K sub D times N theta. K sub D is the rate constant. N theta is the number of this Rm. In this case, the 7 red spheres absorbed on the surface already. Alright, so N theta is the number of occupied sites. And again, theta is the fractional coverage. D theta over dt can be expressed as, well, the rate of adsorption minus the rate of desorption. When adsorption and desorption reach equilibrium, d theta over dt is 0. Therefore, this minus this is 0. The adsorption rate is equal to the desorption rate at equilibrium. Again, when we have a equilibrium between adsorption and desorption, we have Ka, the rate constant for adsorption, times P, the pressure of the gas molecules, times N times 1 minus theta. N times 1 minus theta is the number of unoccupied sites. Now the desorption rate, K sub D, is the rate constant, and times theta is the number of occupied sites. The uppercase N and N cancel. N is the total number of sites. Now we have this equation. We can reorganize this equation. So KAP is equal to KD theta plus KAP theta. I'm moving theta to the right hand side of the equation. Now we can obtain the value or the expression of theta at equilibrium. Theta is simply KAP over this KAP plus KD. That's the expression of theta at equilibrium. This is the so-called Langmuir isotherm equation right over here. And then we can just have both the denominator and the numerator divided by K sub D. On top we have K over KdP. On the bottom we have K over KdP plus 1. And then we define the equilibrium constant for the adsorption-desorption process. So this uppercase K is the equilibrium constant. It's the forward rate constant over the reverse rate constant. So in this case, it's K sub A over K sub D. Now the expression of theta is really simple. It's Kp over Kp plus 1. You can see this is almost always less than 1. Alright, so you can see this Kp on top, Kp plus 1 on the bottom, and therefore this has to be less than 1. Unless K is 0 or P is 0. Alright. Now we have this equation. What if we have experimental data of the value of theta at equilibrium and P at equilibrium? How do we analyze this equation? Well, apparently this equation is not linear equation. Theta is not linear with P. But if we take the reciprocals of both sides, then we have 1 over theta is equal to Kp plus 1 over Kp. And this is just 1 plus 1 over K times 1 over P. So now you can see 1 over theta is linear with 1 over P. We can plot 1 over theta versus 1 over P. The slope is going to be 1 over K. The intercept is just 1. So over here we have a simple graph of 1 over theta versus 1 over P. We have a slope of 1 over equilibrium constant, intercept of 1. This is also one of those double reciprocal plot. Let's look at one numerical example problem, 13.5.1. Let's look at this Langmuir isotherm equation. At equilibrium, theta is Kap over Kap plus Kd, and it can be written as Kp over Kp plus 1. This K is uppercase. The uppercase K is the equilibrium constant for the adsorption-desorption process. And this uppercase K is equal to the lowercase K sub A over the lowercase K sub D. The adsorption rate constant divided by the desorption rate constant. And now we take the reciprocal of both sides. 1 over theta is Kp plus 1 over Kp. And 1 over theta is simply 1 plus 1 over K times 1 over P. By the way, why do we want to take the reciprocal of both sides? Well, it's just because we cannot separate Kp plus 1 in the denominator, but now we can separate this too, as the sum is in the numerator. We can separate this too. This is just a common technique for data analysis. So now let's have some experimental data. Let's say when pressure is 0.01 bar, theta is 0.2. When pressure is 0.02 bars, theta is 0.3333. Now let's make a plot over here and then determine the slope. The slope is going to be 1 over the equilibrium constant K. So we can actually make the graph. We can also do hand calculation. The slope is simply delta y over delta x. So on top we have delta y. Delta y is the difference between this 1 over theta values. On the bottom we have the change or the difference in 1 over p. So on top we have 1 over theta minus 1 over theta. On the bottom we have 1 over p minus 1 over p. Okay, this is the change of 1 over p. On top the change of 1 over theta. Do the calculation, we get 0.04, and therefore we determine the equilibrium constant K is just 25. Or you can say the rate constant of adsorption over the rate constant of desorption is 25. In some cases, adsorption is accompanied by the dissociation of the adsorbate. For example, H2 may decompose on the surface and occupy 2 adsorption sites. So over here we have 2 equations. One is this R2, for example, a diatomic molecule reacting with 2 unoccupied sites to form 2Rm, and 2Rm can become this R2 in the gas phase, and then 2 unoccupied sites. Alright, in this case we can still write out the expression of d theta over dt. Again, what's the meaning of theta? Theta is the percentage of the occupied site. How does that change? Well, over here we have the adsorption rate minus desorption rate. The adsorption rate is the rate constant times P, which is the pressure of this R2, and then times over here there's a coefficient 2 here, so we need to have the number of unoccupied sites squared. Alright, and then over here it's K sub D, the rate constant, times this is the occupied sites, and theta squared. Because of the coefficient 2, it has to be squared. At equilibrium, d theta over dt is 0, therefore this adsorption rate minus desorption rate is just 0. This equals this. We take the reciprocal of both sides, we get the square root. We take the square root of both sides, and then we get the square root of k times p, and then multiply by 1 minus theta equals the square root of kd, and then times theta. Now again, this uppercase K is the equilibrium constant for the adsorption desorption process. The uppercase K is the rate constant K sub A over the rate constant K sub D. Alright, and then we have this equation, the square root of Kp times 1 minus theta equals theta. We reorganize this equation. Theta is the square root of Kp over the square root of Kp plus 1. And again, we can see this is very likely smaller than 1 because Kp are typically just positive. K is always positive and P is usually positive. Alright, P can be 0. That means if we have 0 concentration of R2 and then P is 0, right? But usually P is positive and theta is less than 1. And again, this K is the equilibrium constant. It's equal to the forward rate constant over the reverse rate constant. In this case, adsorption over desorption. And this time, we need to actually make a plot of 1 over theta versus 1 over the square root of P. Because we can take the reciprocals of both sides of this equation, and 1 over theta is the square root of Kp plus 1 over the square root of Kp. So 1 over theta is 1 plus 1 over the square root of K times 1 over the square root of P. So in this case, 1 over theta is linear to 1 over the square root of P. We make this kind of graph, 1 over theta versus 1 over the square root of P. The slope is 1 over the square root of K. The intercept is 1. Chapter 13, Complex Reaction Mechanisms. Section 13.6, Catalysis. A catalyst lowers the forward and reverse energy barriers, and consequently increases the forward and reverse reaction rates. But a catalyst never changes the chemical equilibrium. The chemical equilibrium is determined given the Gibbs energy of formation of the products and the Gibbs energy of formation of the reactants at a given temperature. And therefore, the equilibrium constant never depends on the existence of the catalyst. Enzymes are proteins that catalyze biochemical reactions. Therefore, enzymes are also catalysts. The simplified enzyme catalytic mechanism involves 3 elementary steps: from the substrate and a free enzyme to the enzyme substrate complex. The ES complex may decompose back to a free substrate molecule and a free enzyme. The ES complex can also react to produce a product P and release a free enzyme. The free enzyme can then react with another substrate. S denotes the substrate in this equation. E is the enzyme. P is the product. ES is the enzyme substrate complex. We have 3 rate constants for the three elementary steps. K1 is the rate constant from S plus E to ES. K minus 1 is the rate constant from ES to a separate S and E. K2 is the rate constant from ES to P plus E. K2 is also called the turnover number of the enzyme. A catalyst increases the forward and reverse reaction rates by lowering the reaction barrier, but a catalyst never changes the chemical equilibrium. Enzymes are proteins that catalyze biochemical reactions, and a simplified enzyme catalytic mechanism involves only three elementary steps. So S and E form ES, ES may decompose back to S plus E, and ES may proceed to produce the product P and release a free enzyme. So this diagram shows you how enzyme can lower the barrier. Without the enzyme, the substrates may overcome a larger NH barrier and form the products. On top of this barrier, we have the transition state that connects the reactants and products. In the enzyme catalyzed reaction, the reactants are called substrates. And also, with some enzyme in the system, the substrate may combine with enzyme to form the ES complex, the enzyme substrate complex. The ES complex may overcome a smaller NH barrier to form a complex between the enzyme and the product. And this EP decomposes into products and a free enzyme quickly. So sometimes we can ignore this small dip over here. We'll just assume this ES go through a lower NH barrier and form the products and release a free enzyme directly without worrying the formation of the EP complex. So again, this is just a simplified enzyme catalytic mechanism. The simplified enzyme catalytic mechanism involves only three elementary steps, from S plus E to ES, from ES back to S plus E, and from ES to P plus E. P denotes the product. The overall reaction rate is the production rate of P. So the rate is dP over dt. And P is involved in only one elementary step. Over here, the rate is K2 times the concentration of ES. Now we need to determine the expression of the concentration of ES. If the ES complex is unstable with much higher energy than E plus S and E plus P, which is fairly common, we can make steady-state approximation for the ES complex. dES over dt equals 0. That's the steady-state approximation. The idea behind this is the concentration of the ES complex is extremely low throughout the reaction. Therefore, dES over dt is very small, and then we make approximation. This is approximately 0. Now we need to write out the differential equation for this dES over dt. ES is produced in the first step, consumed in the second and third steps. In the first step, the production rate of ES is K1 times S times E, right here. In the second step, the consumption rate of ES is K minus 1 times ES, here. And then the third step, the consumption rate of ES is K2 times ES, here. Now, making the steady state approximation, we have this equals 0, and now we have the expression of the complex ES. It's just K1 SE over K minus 1 plus K2. It looks complex, so we define a composite constant, so-called Michaelis-Menten composite constant, uppercase K sub m equals K minus 1 plus K2 over K1. So we can rewrite the concentration of the ES complex as S times E over K sub m. Again, this K sub m is the Michaelis-Menten composite constant. Now the reaction rate is dP over dt equals K2 ES, and ES is S times E over Km. And we have this equation. So this K sub m is almost the pseudo equilibrium constant for the reaction from the ES complex to separate S and E. Now the substrate may exist in three different forms. We can have the substrate in its free form, a free substrate, in a complex, or already converted to P. Therefore, we have this equation: S plus ES plus P is equal to S naught. S naught is the initial concentration of the substrate. So this substrate may stay in its free form, may be converted to the ES complex, may be converted to the product. So we have this equation. And the enzyme may be either free or in the ES complex. So the initial concentration of the enzyme is equal to, in the sum of the enzyme and the enzyme substrate complex, sum of this two is equal to the initial concentration of the enzyme. And now we can rewrite this equation. S is S naught minus P minus ES, and E is E naught minus ES. So we have a more complex equation, but by doing so we reduced some variables. Because S and E are variables, at least we do not see those variables. However, there are still too many variables. At the very stage of the reaction, we may assume this P is negligible, or P is much smaller than these two terms. So we can further simplify this equation by assuming P is 0, or very close to 0. We neglect this P. Now we have this equation: the Michaelis-Menten composite constant times the concentration of the ES complex equals the product of these two terms. One is S naught minus ES, the other is E naught minus ES. Now by looking at this equation, it seems we have only one variable, that's ES. We can solve for it, but we can further make approximations to further simplify this, because the concentration of the ES complex is usually much smaller than the initial concentration of the substrate. We will just replace this with S naught. Again, ES is much smaller than S naught. So we have an even simpler equation like this. Now we expand this by multiplying S0 and E0 over here, S0 and ES over here. This equation contains only three terms: 1, 2, 3. Two of the three terms contains the concentration of ES. We can put them together and derive the expression of the concentration of ES. The concentration of ES is just E naught S naught divided by S naught from here plus Km from here. So this is the expression for the concentration of the enzyme substrate complex at the very early stage of the reaction, assuming P is negligible and ES is much smaller than S naught. The reaction rate at the initial stage of the reaction is therefore K2 times ES, and we plug this in here. It's K2 E naught S naught over S naught plus Km. Again, this R sub naught is the initial reaction rate. This 0 reminds us we're talking about the reaction rate at the beginning of the reaction. It's hard to analyze this expression because we cannot separate this two on the bottom. So one idea is to take the reciprocal of both sides of this equation. 1 over R naught now is equal to the sum of two terms. We have S naught divided by the top and we have Km divided by the top. When we use Km divided by the top K2 E naught S naught, we have this expression. When we use S naught divided by K2 E naught S naught, we get this expression. So now if you just examine this equation, it's a linear equation. If you consider this 1 over R naught as y, 1 over S naught as x, and then y is equal to the slope times x plus the intercept. Again, we have this equation. R naught depends on S naught, but the dependence is not directly linear. We have to take the reciprocals of R naught. We get this expression. So 1 over R naught is linear to 1 over S naught, and Km over K2 E naught is the slope. 1 over K2 E naught is the intercept. So that means we can plot 1 over R naught versus 1 over S naught and do a linear regression to determine the slope, which is this, and the intercept, which is 1 over K2 E naught. When the concentration of the substrate is infinity, 1 over the concentration is 0. And then we simplify this equation to here. 1 over R naught approaches 1 over K2 E naught when the initial concentration of the substrate approaches infinity. And this is going to be the maximum reaction rate we can achieve with a infinity amount of substrate. Again, R naught approaches K2 E naught when this S naught approaches infinity. Now we define R sub max to be K2 E naught because this is the maximum reaction rate that's achieved only when S naught is infinity. So we can further simplify this equation because K2 E naught is R max. This K2 E naught is R max. Now 1 over R naught is linear to 1 over S naught. The slope is Km over R max. The intercept is 1 over R max. And we can plot 1 over R naught versus 1 over S naught. And this is a double reciprocal plot. This plot is called the Lineweaver-Burke plot. In this plot, the slope is Km over R max. The y-intercept is 1 over R max. R max is just K2 E naught. The Michaelis-Menten composite constant K sub m is equal to the slope divided by the y-intercept. So again, it's pretty simple. You just need to make a graph of 1 over R naught versus 1 over S naught, and then do a linear regression, get a linear equation, get the slope. The slope is Km over R max. Get the intercept. The intercept is 1 over R max. You can see the slope divided by the intercept is just K sub m, the Michaelis-Menten composite constant. The reciprocal of the y-intercept is R max. So again, let's look at the Lineweaver-Burke 1 over R naught versus 1 over S naught reciprocal plot, or double reciprocal plot. 1 over R naught is the vertical axis, 1 over S naught is the horizontal axis. If we have multiple experimental data, we can plot all of them. It looks linear. We can determine the y-intercept, which is 1 over R max. The slope is Km over R max. Now let's look at one numerical example problem. 13.6.1. Calculate R max and K sub m given the following data. There are only 2 data points, so we don't have to generate a graph. We can compute the slope and intercept by hand. But first, we need to get the reciprocals of R naught and also the reciprocal of S naught. They are here, also tabulated. And then just imagine if we plot 1 over R naught as the vertical axis, 1 over S naught as the horizontal axis, The slope is simply the difference between these two divided by the difference between these two. So here, this is the slope. The slope is km over r max, and it's 500 minus 250 divided by 1000 minus 200. So the slope is 0.3125 second, and that's km over r max. Now we can compute the intercept. The intercept is simply the value of y, the vertical axis, 500, minus the slope times the horizontal axis. This is the slope, this is the value of x, the horizontal axis. We get 187.5 second per molar. And therefore, we just take the reciprocal of this, we get our max 0.005333 molar per second. That's the maximum reaction rate when the concentration of the substrate approaches infinity. What about this Michaelis-Menten composite constant? Well, it's simply the slope divided by the intercept. Well, so it's just 0.3125 over 187.5. The result is 0.001667 molar. And this is the Michaelis-Menten composite constant. The enzyme catalysis can be generalized. So the catalyst does not have to be an enzyme. It can be just any catalyst. In that situation, we'll just use C instead of E in the mechanism, and C denotes the catalyst. We still use a S to denote the reactant or substrate, P the product. And we have the same rate constant notations, K1, K minus 1, and K2. K2 is the turnover number of the catalyst. So we can do the similar derivation. It's just we need to replace E, the enzyme, with C, the catalyst. And then we can get the expression of SC complex. That's S times C over the Michaelis-Menten composite constant. And this case of M is K minus 1 plus K2 over K1 over here. Reaction rate is dP over dt. It's K2 times SC over here. It's K2 SC over Km, because this is the expression of the concentration of the SC complex. Just like the enzyme catalysis, we can do similar derivation and get the reciprocal of the initial reaction rate. 1 over R naught is linear to 1 over S naught. The slope is Km over R max. The intercept is 1 over R max. And R max is K2 times C naught. C naught is the initial concentration of the catalyst. Chapter 13, Complex Reaction Mechanisms. Section 13.7, Radical Chain Reactions and Radical Chain Polymerization. Radicals are chemical species that contain at least one unpaired electron, such as the hydrogen radical and the hydroxide radical. In the hydrogen radical, we have only one electron, unpaired. In the hydroxide radical, we have a total of 9 electrons. 8 of them are paired, but there's also one unpaired electron. Radicals are often highly reactive. An example of radical-mediated reaction is the thermal decomposition of ethane in the gas phase. So ethane may decompose and form ethylene and H2. The complex mechanism of this reaction may involve 3 stages: initiation, propagation, and termination. In the initiation stage, radicals are produced. In the propagation stage, the number of radicals remain unchanged, but the identity of the radical may change. Termination. Radicals are annihilated in this stage. So now let's look at the three different stages of the thermal decomposition of ethane. Initiation. So it's possible to heat up this molecule and break the carbon-carbon hydrogen bond. If we create two radicals at the same time, those are two methyl radicals. Propagation. There are three important propagation reactions. The methyl radical may attack a ethane molecule and abstract a hydrogen off to form CH4 methane. And now we have a different radical, an ethyl radical, C2H5. C2H5 may decompose into ethylene and a hydrogen radical. Now the hydrogen radical can also attack a ethane molecule to form H2 and another ethyl radical. And again, this ethyl radical may decompose into ethylene and a hydrogen radical. In the termination stage, radicals are annihilated. But how? Usually you have two radicals reacting with each other, and then all electrons are paired. For example, the hydrogen radical and the ethyl radical may form ethane, or the hydrogen radical may attack this ethyl radical, take away one hydrogen atom and form H2 and then ethylene. By the way, this hydrogen radical is just the hydrogen atom. There are three radicals involved in the thermal decomposition of ethane: the hydrogen radical, the methyl radical, and the ethyl radical. Now we can make steady-state approximation to these three radicals. dH over dt is 0, the methyl over dt is 0, the ethyl over dt is 0. Well, this is just because radicals are often highly unstable. The concentrations of these radicals are often extremely low, and then we can make these approximations. Using the three equations, we can simplify the differential equations and then express the reaction rate in terms of a constant times the concentration of C2H6. The derivation is non-trivial, it's skipped here, it involves a lot of mathematical detail. I just want to show you, in the end, the consumption rate of C2H6 can be expressed as a constant times its concentration. And now, what are this K1, K3, K4, K5, K6? Alright, it's from the previous page. We have K1 here for initiation, K2, K3, K4 are the propagation steps, K5 and K6 are the termination steps. So we got all those over here combined to form this effective rate constant. So this is a complex reaction mechanism, and we have to use the steady-state approximation to solve the differential equations approximately and get this integrated the rate law, and then we can integrate these equations to get the integrated rate law, and this is a pseudo first order reaction. Now let's look at this reaction again. This reaction may also occur in a single elementary step. How is that possible? Well, if you just compare the reactant and the product, well, we just need to break two carbon-hydrogen bonds and form one new hydrogen-hydrogen bond, and then we have the products. So it's possible to draw the transition state structure for this reaction. The transition state should have two partially broken carbon-hydrogen bonds and one partially formed hydrogen-hydrogen bond. And also, well, there should be a carbon-carbon pi bond being partially formed. Sorry about the typo. This should be partially formed. This elementary step has overall a larger reaction barrier than the previously studied complex mechanism, and therefore it has a smaller reaction rate, K sub 7. So this K sub 7 is much smaller than this K sub effective. But if we consider both pathways in parallel, the overall reaction rate should be this. We have K effective plus K7 multiplied by the concentration of SN. But again, keep this in mind, this K7 is much smaller than K effective. So this K7 can be even neglected. But overall, even if we have this expression, it's still a pseudo first order reaction. Combustion reactions are often radical chain reactions. Now let's look at the combustion of methane in oxygen. Also, there are 3 stages: initiation, propagation, termination. In the initiation stage, radicals are produced. In the propagation stage, the number of radicals remains unchanged. In the termination stage, radicals are annihilated. Initiation. So it's possible for one of the carbon-hydrogen bonds to break and form methyl radical and hydrogen radical. With enough energy, we can even break a oxygen-oxygen double bond in O2 to form 2 oxygen atoms. Propagation. A hydrogen radical may attack a methane molecule and abstract one hydrogen off to form H2. That leaves a methyl radical. The hydrogen radical can also react with oxygen 2 to form hydroxide and an oxygen atom. Hydroxide can attack a methyl molecule to form another methyl radical and water. The methyl radicals can react with the oxygen atom to form formaldehyde and hydrogen atom. Formaldehyde may react with hydroxide to get another radical and water. So all those propagation elementary steps involve the change of the identity of the radicals, but usually the number of radicals remains unchanged. So if you have one radical on the left hand side, you see a radical on the right hand side. It's just these 2 radicals are different. You see one radical on the left and then one radical on the right. It's just the identity changes. Termination. It's possible for 2 radicals to form a single bond in between. So the R radical and the hydrogen atom may form RH and release energy. The energy must be taken away by a medium molecule denoted by M. M star denotes the energized medium. Now let's look at radical chain polymerization. It's the polymerization of monomers initiated by radicals. How do we make radicals in the first place? We need radical initiators in this kind of polymerization reactions. Now let's look at the initiation stage. We need a so-called radical initiator and decompose that into 2 radicals. So it's this elementary step from the initiator I to 2 radicals R. The rate constant is K sub I. I stands for initiation. For example, benzoyl peroxide is often used as the radical initiator that initiates the radical chain polymerization. The structure is like this. You have a benzene here and then COO functional group. Same here, benzene COO functional group. And then in the middle, there's a single bond between this COO and this COO. The structure looks like this: 2 benzene rings, 2 carbonyl groups, and in the middle you have oxygen single bonded to oxygen. So it's called peroxide. Between these 2 oxygen, the bond is weak due to the repulsion between all those lone pair electrons on the oxygen atoms. So if you heat it, it's going to break the oxygen-oxygen bond to form 2 radicals. And now we have radicals. The radicals may attack the monomers So here, a radical reacts with a monomer to form a single bond with the monomer, and it becomes another radical. K1 is the rate constant for this activation step. Here's one example. We can use this radical to attack an ethylene molecule. Now we have a single bond between this oxygen and one of the two carbons in ethylene right here. And then we have, well, a new radical. It's benzene, COO, CH2, CH2 radical. So the terminal carbon on the right hand side is a radical with one unpaired electron. Now propagation. So once we have a Rm radical, it may react with another monomer to form RMM radical, which then attack another monomer to form RMMM radical. Now we have 3 monomer units in the polymer. And then we have Rm with n-1 units reacting with another monomer, we have n units. And in general, we use a rate constant K sub p to denote the rate constant for all these reactions because they are similar. It's just a M radical attacking another M, a M radical reacting with another M. Over here, N is just the length of the polymer chain, and again Kp is the rate constant for propagation. K sub p is approximately independent of the polymer length. Now let's look at a few examples. This is the radical reacting with a ethylene. We form this radical. It can react with another ethylene, and now we have a longer carbon chain. And then this longer carbon chain react with another ethylene. We have a even longer carbon chain that contains now 3 ethylene units. Termination involves the recombination between 2 radicals. For example, if we have 2 polymer radical chains with a unit length of N and M, well, these 2 radicals, these 2 unpaired electrons may form a single bond in between. Now we have a polymer with a unit length of M plus M. The rate constant is denoted by K sub T. T stands for termination. Here's an example for termination. So if you have a radical chain with 5 monomer units reacting with another radical chain with 4 monomer units, you can get a polymer with a total of 9 monomer units in the middle. Now we're going to study the mechanism of the radical polymerization. We'll treat all radicals as a whole for convenience. We're going to use this notation. This is Rmx. M sub x means we have x monomer units, and this x can be 0, 1, 2, 3. So when I write this, it means we have a R radical, we have Rm radical, RMM radical, RMMM radical, RMMM radical, etc. All of those are denoted by this because they have similar chemical properties. Now the number of these radicals is not affected by the activation reaction or the propagation reaction, because at the activation stage you start from a R radical reacting with an M and you form Rm radical. The number of radicals is not changed. In the propagation also, the number of radicals is not changed. Alright? The number of radicals is changed only in the initiation stage and in the termination stage. In the initiation reactions, the number of radicals increases. In the termination reactions, the number of radicals decreases. The radicals are produced in the initiation step. So let's look at this equation. We can see 2 R radicals are produced, and the production rate is 2 times Ki times I, and then multiplied by phi. So why is that? First, we understand the reaction rate is Ki times the concentration of I, so right here. Well, but when 1 I is consumed, we generate 2 R, so we need a 2 here. And also, not every single R can initiate a radical chain reaction. Sometimes this R radical is immediately annihilated for some reason. So here we need to have a new parameter phi. Phi is the probability of R naught or R dot or R radical successfully initiating a radical chain. So that's why what this phi is stands for. Phi is usually lower than 1. The radicals are consumed in the termination reactions. So over here, 2 radicals are annihilated at the same time. So the consumption rate of the radicals is -2 K sub T times this squared. Again, we're just treating both M and N as X. X is just more general. We treat this as Rmx, we treat this as Rmx. So again, we're using Rmx as the total concentration of all those radicals. Now we're going to use the steady state approximation to all those radicals. That means the production rate of the radicals is equal to the annihilation rate of the radicals. So we have this 2 phi Kii on the left equals this 2 kT radical squared on the right. So by looking at this equation, we can express the concentration of all radicals easily. 2 and 2 cancel, you move kT to the left hand side and then take the square root. So the concentration of all radicals should be the square root of phi Ki over kT times the concentration of I. Now monomers are consumed in the activation step and also the propagation step. It is also reasonable to assume this K1 is very close to Kp, because if we look at those reactions, they are all reactions between a radical and a monomer, a radical and a monomer. So overall, the consumption rate of M can be considered as negative Kp times M times the total concentration of all radicals. And again, this X can be 0, 1, 2, 3, 4, or 5, or 6, etc. And also we have the expression of this concentration of all radicals from the previous page. It's the square root of phi Ki over Kti. So we plug in that expression, phi Ki over Kti over here. And this is the consumption rate of the monomers, or how fast the monomers are consumed per unit time. The average kinetic chain length for the radical chain polymerization is defined as this. Average kinetic chain length, it's the consumption rate of M of the monomers divided by the production rate of the radicals. So we have the consumption rate of the monomers on top, and we have the production rate of the radicals on the bottom. So it's from 1I to 2R radicals with a rate constant of K sub I and a efficiency of phi. So we have this equation. Now we can clean it up. We get expression for the average kinetic chain length You just see we have square root of I on top, I on the bottom, square root of ki on top, ki on the bottom, square root of phi on top, and phi on the bottom. So after we clean up this expression, in the end we have this. The average kinetic channel length is kpm over 2 times the square root of phi ki kti. So what's the meaning of this? Well, the average kinetic channel length is this. So assuming within a second 1,000 monomers are consumed, 10 radicals are produced. We're just assuming, this 1,000 monomers are attached to those 10 radicals, and then each radical has a chain length of 1,000 over 10. That's 100. So that's the physical meaning of it. And why do we even care about this average kinetic chain length? Because this is a instantaneous property. So at given time you have this average kinetic chain length, and then a different time you have a different average kinetic chain length. Although this average kinetic chain length changes with time, but overall it gives us a rough understanding of the final average chain length of the polymers. So that's very useful. And we can determine the average kinetic chain length with all those rate constants, the concentration of the monomers, the concentration of the initiator, and also this efficiency phi here. Phi is less than 1. Now we can analyze the average kinetic chain length qualitatively as well. When m is larger, you have a longer chain length. When I is smaller, you have a longer chain length. And also, if Kp, the propagation rate constant, is larger, you have a larger chain length. But if the initiation rate constant and the termination rate constant are large, you have a shorter kinetic chain length. Chapter 13, Complex Reaction Mechanisms, Section 13.8, Oscillating Reactions. There are many types of oscillating reactions. The Briggs-Rauscher reaction is one of them. The reaction system contains hydrogen peroxide, an iodate, manganese 2+ as catalyst. There's sulfuric acid, and also we have this organic molecule, propane 1,3-dioic acid, with an active hydrogen atom which can reduce iodine 2 to iodide. Iodide is colorless. Iodine is amber color in water. The reaction is this. So over here we have propane 1,3-dioic acid reacting with the iodine molecule, and you can see one of the hydrogen is replaced by iodine, and it will produce iodide minus and H plus. Iodine 2 and iodide may combine to produce triiodide, and starch is added in the solution as a color indicator because starch turns triiodide dark blue. Now let's watch part of the video. Now we have iodine in the solution. It's amber color. Now it turns dark blue due to the formation of triiodide. Now it's amber again, dark blue. Now clear. We can also measure the concentration of iodide in the solution. It oscillates. Eventually it dies down at equilibrium. Chapter 13, Complex Reaction Mechanisms, Section 13.9 Electron Transfer Reactions. There are many types of electron transfer reactions that involve different mechanisms. Here we introduce three common types of electron transfer reactions. Number 1, inner sphere electron transfer in a solution. Number 2, outer sphere electron transfer in a solution. Number 3, heterogeneous electron transfer between a solution and a solid. So first, inner sphere electron transfer in a solution. In a solution, we may have different transition metal complexes, and then two redox centers may be connected via covalent bonds during the electron transfer. For example, in an aqueous solution, we may have these two transition metal complexes, and it's possible for this chlorine or chloride ligand to connect this cobalt center and this chromium center, and this electron transfer occurs through this chloride ligand bridge, and it's called inner sphere electron transfer in a solution. Again, there's a bridge from cobalt to chlorine to chromium. And the second type is the outer sphere electron transfer in a solution. In this case, again, we have two transition metal complexes with two metal centers. These two metal centers may undergo redox reactions, but in this case, the two redox centers are not connected via bonds. Electrons hop from one center to another. Markov theory proposes this mechanism. You have an electron donor denoted by D, electron acceptor denoted by A. They get really close to each other, but there's no bond between these two complexes. And then electron hops from D to A, from the donor to the acceptor. Now D becomes D plus, A becomes A minus, and then they separate. Again, D and A stand for electron donor and acceptor. One example is the reduction of iron 3 by iron 2 in water. So we have these two transition metal complexes. We have this iron 2 plus, iron 3 plus, and they get close to each other, and then an electron may hop from this iron 2 to iron 3. And then this iron 2 becomes iron 3, this iron 3 becomes iron 2. Now the third type, heterogeneous electron transfer between a solution and a solid. Because we have a liquid phase, we have a solid phase, this is called heterogeneous electron transfer. Here's one example. If we have a zinc copper electrochemical cell, we have a zinc electrode, we have a copper electrode. So this zinc and this copper are in the solid state. However, they are also immersed in a solution. And over here, zinc may lose 2 electrons to form zinc 2 plus, and then dissolved in the solution. On the right hand side, copper 2 plus may get 2 electrons and form a copper atom deposited on the copper electrode.